Welcome to our deep dive into one of the most intriguing and controversial topics in modern astrophysics, the axis of evil. Today, we'll explore what this mysterious anomaly is, why it has sparked so much debate, and what it could mean for our understanding of the universe. The axis of evil refers to an unexpected alignment in the cosmic microwave background, or CMB. The CMB is the afterglow of the Big Bang, a faint radiation that fills the universe and provides a snapshot of the early cosmos. Studying this radiation has given us invaluable insights into the origins and structure of the universe. When scientists first mapped the CMB, they expected to see tiny fluctuations spread uniformly across the sky. These fluctuations represent slight differences in temperature that trace the density variations in the early universe. However, what they found was something quite unexpected and puzzling. In 2005, researchers analyzing data from the Wilkinson Microwave Anisotropy probe, or WMAP, discovered that these temperature fluctuations were not as random as predicted. Instead, they seemed to align along a specific direction in space. This alignment came to be known as the axis of evil, a term coined to highlight its disruptive implications for cosmological theories. The discovery of the axis of evil challenged a fundamental assumption in cosmology, the principle of isotropy. This principle states that the universe should look the same in all directions when viewed on a large scale. If the axis of evil is real, it suggests that this assumption might not hold true, shaking the foundations of our understanding of the cosmos. The significance of this alignment cannot be overstated. If the axis of evil is not a fluke or an artifact of our observations, it could imply new physics beyond our current models. It might suggest that our universe has a preferred direction, or that there are unknown factors influencing the CMB that we have yet to discover. Since its discovery, the axis of evil has been the subject of intense scrutiny and debate. Scientists have proposed various explanations, ranging from data processing errors to foreground interference, and even more exotic theories involving the shape and topology of the universe itself. Despite these efforts, no consensus has been reached. To understand why this alignment is so controversial, we need to delve deeper into how the CMB is measured and analyzed. Instruments like WMAP and its successor, the Planck satellite, are designed to capture incredibly detailed maps of the sky. The precision of these measurements is crucial for detecting and interpreting anomalies like the axis of evil. The process involves meticulous calibration and complex data processing to remove any distortions caused by the instruments or other sources of radiation. Even with the most careful analysis, distinguishing between genuine cosmic signals and artifacts can be extraordinarily challenging. As we continue to explore the axis of evil, we must remain open to new data and interpretations. The ongoing advancements in observational technology and data analysis promise to shed more light on this enigmatic feature of the CMB. Whether it turns out to be a fundamental aspect of our universe or a subtle error in our measurements, the pursuit of understanding it drives the progress of astrophysics. The cosmic microwave background, or CMB, is often described as the afterglow of the Big Bang. This faint radiation permeates the entire universe, offering a glimpse into its earliest moments. Discovered in 1965 by Arno Penzias and Robert Wilson, the CMB has since become a cornerstone of cosmological research. The CMB is essentially a snapshot of the universe when it was just 380,000 years old. At that time, the universe had cooled enough for protons and electrons to combine and form neutral hydrogen atoms. This process released photons, which have been traveling through space ever since. These ancient photons have been stretched to microwave wavelengths by the expansion of the universe. By studying the CMB, scientists can learn about the conditions of the early universe and the processes that shaped its evolution. The uniformity of the CMB provides evidence for the Big Bang theory. However, the CMB is not perfectly uniform. Tiny fluctuations in temperature are observed, representing slight differences in density in the early universe. These fluctuations are crucial for understanding the formation of large-scale structures like galaxies and clusters. To map the CMB, scientists use satellites equipped with sensitive detectors. These instruments measure the temperature of the CMB across the entire sky with incredible precision. The Wilkinson Microwave Anisotropy probe, or WMAP, was one of the first missions to provide detailed maps of the CMB. WMAP's observations revealed the small temperature fluctuations in the CMB, allowing scientists to refine their models of the universe's history. The data from WMAP helped establish the standard model of cosmology, which includes components like dark matter and dark energy. Following WMAP, the Planck satellite took over the task of mapping the CMB with even greater precision. Launched by the European Space Agency, Planck provided the most detailed images of the CMB to date. Its findings have further solidified our understanding of the universe's early stages. Planck's data confirmed many of WMAP's results, but also revealed new features, such as the axis of evil. These high-resolution maps of the CMB allow researchers to study the universe's properties with unprecedented accuracy. The Planck mission's contributions are invaluable to cosmology. The CMB's uniformity and the slight deviations within it tell us about the universe's origins and its large-scale structure. These measurements have also provided a wealth of information about the universe's age, composition, and rate of expansion. The study of the CMB continues to be a rich field for scientific discovery. One of the most intriguing aspects of the CMB is its power spectrum, which shows how temperature fluctuations vary with scale. The peaks in the power spectrum correspond to different physical processes in the early universe. Analyzing this spectrum helps scientists understand the physics of the early cosmos. The CMB also carries information about the universe's geometry. By examining the patterns of fluctuations, researchers can infer whether the universe is flat, open, or closed. Current data suggests that the universe is remarkably flat, supporting the inflationary model of the Big Bang. Furthermore, the CMB is affected by phenomena like the Sunyaev-Zeldovich effect, where the CMB photons interact with hot gas in galaxy clusters. Studying these interactions provides insights into the properties of galaxy clusters and the distribution of matter in the universe. This interplay between the CMB and other cosmic structures enriches our understanding of the cosmos. Another fascinating feature of the CMB is its polarization, which offers additional clues about the early universe. Polarization patterns are generated by scattering processes that occurred when the universe was still very young. These patterns help test theories about cosmic inflation and the early universe's dynamics. The precision of CMB measurements has improved dramatically over the years, thanks to advances in technology and data analysis techniques. Each new generation of instruments provides clearer and more detailed views of the CMB. These improvements continue to drive progress in cosmology, revealing new details about the universe's infancy. As we gather more data from ongoing and future missions, our understanding of the CMB and its implications will deepen. The study of the CMB remains a central and dynamic area of research in astrophysics. Each discovery brings us closer to unraveling the mysteries of the universe's origin and evolution. The initial observations of the cosmic microwave background were a monumental moment in astrophysics. Arno Penzias and Robert Wilson were the first to detect this faint radiation in 1965. Their discovery was accidental, made while working with a radio antenna at Bell Labs. At first, Penzias and Wilson thought the noise they detected was due to technical issues or bird droppings on the antenna. After ruling out these possibilities, they realized they had found something extraordinary. This noise turned out to be the thermal radiation left over from the Big Bang. This discovery confirmed the theoretical predictions made decades earlier by scientists like George Gamow and Ralph Alpher. Their work suggested that the early universe was hot and dense, and as it expanded, it would leave behind a faint glow. Penzias and Wilson's findings provided the first observational evidence for this theory. The initial measurements showed the CMB to be remarkably uniform, with only slight variations in temperature. These tiny fluctuations were crucial, as they represented the seeds of all current structures in the universe. Early observations were limited by the technology of the time, but still incredibly valuable. Subsequent experiments aimed to map the CMB more precisely. The Cosmic Background Explorer, or COBE, launched in 1989, was a major step forward. COBE confirmed the CMB's uniformity and measured its spectrum with great accuracy. COBE's data revealed the first detailed maps of the CMB's temperature fluctuations. These maps showed that the universe's early density variations led to the formation of galaxies and clusters. This was a significant breakthrough in understanding the universe's large-scale structure. The success of COBE set the stage for more advanced missions like the Wilkinson Microwave Anisotropy probe. WMAP, launched in 2001, provided much higher resolution images of the CMB. These observations refined our understanding of the universe's age, composition, and development. WMAP's data allowed scientists to measure the universe's parameters with unprecedented precision. The improved resolution revealed finer details in the CMB's fluctuations. These details helped to confirm the standard model of cosmology and provided insights into the nature of dark matter and dark energy. Planck, launched by the European Space Agency in 2009, took these observations even further. With its superior sensitivity and resolution, Planck produced the most detailed maps of the CMB to date. Planck's findings have been essential in refining cosmological models. The initial observations by Penzias and Wilson laid the groundwork for all subsequent studies of the CMB. Each new mission has built on the previous ones, providing more detailed and accurate data. These observations have been crucial in shaping our understanding of the universe. Early CMB observations also revealed unexpected features like the axis of evil. These anomalies have sparked ongoing debates and further investigations. Understanding these anomalies is key to comprehending the universe's true nature. The importance of initial observations cannot be overstated. They provided the first direct evidence of the Big Bang and opened up new avenues of research. The discovery of the CMB was a turning point in cosmology, revolutionizing our understanding of the universe. As technology has advanced, so too has our ability to observe the CMB in greater detail. Each new observation brings us closer to answering fundamental questions about the cosmos. The legacy of those initial discoveries continues to drive progress in astrophysics. The pioneering work of early observers has paved the way for modern cosmology. Their discoveries have inspired countless scientists to explore the mysteries of the universe. The journey that began with the accidental detection of background noise has led to a deeper understanding of our cosmic origins. Continuing to build on these initial observations, future missions will likely uncover even more about the early universe. As we look back on these groundbreaking discoveries, we also look forward to what new data will reveal. The study of the CMB remains a dynamic and evolving field in astrophysics. Arno Penzias and Robert Wilson are the most well-known names associated with the discovery of the cosmic microwave background. Working at Bell Labs, they stumbled upon the CMB in 1965. Their work earned them the Nobel Prize in Physics in 1978. George Gamow, Ralph Alpher, and Robert Herman were key figures in predicting the existence of the CMB. In the 1940s, they developed theories about the early universe. Their predictions laid the groundwork for the eventual discovery. Jim Peebles, a prominent theoretical cosmologist, played a crucial role in interpreting the CMB data. His work has been fundamental in understanding the implications of these observations. Peebles' contributions have earned him numerous accolades, including the Nobel Prize. David Wilkinson and Lyman Page from Princeton University were instrumental in advancing CMB research. They contributed to the design and success of the Wilkinson microwave anisotropy probe. This mission provided high-resolution maps of the CMB. John Mather and George Smoot led the COBE mission, which confirmed the CMB's uniformity. Their work helped solidify the Big Bang theory. Both scientists received the Nobel Prize in Physics in 2006. Charles Bennett was the principal investigator for the WMAP mission. His leadership was pivotal in refining our understanding of the universe's age and composition. Bennett's work has been highly influential in cosmology. Jan Tauber was the project scientist for the Planck mission. Under his guidance, Planck provided the most detailed images of the CMB to date. Tauber's contributions have been essential in advancing CMB studies. Nazareno Mandolesi and Jean-Luc Puget played key roles in the Planck mission as well. They were responsible for the low and high-frequency instruments. Their work ensured the mission's success in capturing precise CMB data. Mark Kamienkowski and Lloyd Knox have contributed significantly to the theoretical understanding of the CMB. Their research helps interpret the data and refine cosmological models. Their work continues to influence current studies. Anthony Lazenby and Richard Batty have also made important contributions to CMB research. They have worked on both observational and theoretical aspects. Their efforts have enhanced our understanding of the early universe. Pioneering scientists like Andrei Sakharov and Yakov Zeldovich made early contributions to the field. They explored the theoretical implications of the CMB. Their foundational work has been built upon by subsequent researchers. Researchers such as Rashid Sunyaev and Zeldovich have provided valuable insights into CMB anisotropies. Their work on the Sunyaev-Zeldovich effect has been particularly influential. This effect describes how CMB photons interact with galaxy clusters. Gary Hinshaw and Nils Halvorsen have been pivotal in analyzing CMB data. Their work on data interpretation has been crucial for deriving cosmological parameters. They continue to contribute to ongoing research in this area. Cavill Moodley and his team have worked on understanding the large-scale structure of the universe through CMB observations. Their research has helped clarify the distribution of matter and energy. Moodley's contributions are vital to modern cosmology. The combined efforts of these scientists have transformed our understanding of the universe. Their discoveries and insights have paved the way for future research. The study of the CMB remains a dynamic and evolving field, thanks to their contributions. The discovery of the cosmic microwave background involved meticulous methodology. Penzias and Wilson used a horn antenna at Bell Labs to detect radio waves from space. Initially, they were troubleshooting what they thought was background noise. They measured the radiation across different frequencies to identify its source. The uniform temperature they observed matched theoretical predictions. This helped them realize they had found a cosmic phenomenon. Subsequent studies required more sophisticated equipment to map the CMB. The Cosmic Background Explorer, or COBE, was one of the first dedicated missions. COBE used differential microwave radiometers to measure temperature differences across the sky. COBE's team ensured precision by carefully calibrating the instruments. This involved comparing the signals from different parts of the sky. They aimed to eliminate any potential sources of error. The Wilkinson Microwave Anisotropy Probe, or WMAP, followed COBE. WMAP orbited the second Lagrange point, providing a stable environment for observations. This mission used highly sensitive radiometers to capture detailed images of the CMB. WMAP's methodology included scanning the sky repeatedly to increase data accuracy. The satellite mapped the sky over several years. This repeated coverage helped refine the measurements. Planck, launched by the European Space Agency, took CMB observation to new heights. Planck used two instruments, the low-frequency instrument and the high-frequency instrument. These covered a broad range of frequencies. The Planck team implemented advanced data processing techniques. They corrected for various noise sources, including instrument and cosmic foregrounds. This thorough approach ensured the highest quality data. Planck's scanning strategy involved rotating the satellite to cover the entire sky. This rotation, combined with its orbit around the Sun, provided comprehensive coverage. The data was then meticulously analyzed to produce detailed maps. Ground-based observatories also played a role in CMB research. Instruments like the Atacama Cosmology Telescope and the South Pole Telescope provided complementary data. These telescopes helped verify and extend findings from space missions. Each stage of CMB research involved improving measurement techniques. Calibration, repeated observations, and advanced processing were crucial. These methods helped isolate the true cosmic signal from background noise. The methodology also included cross-checking results with theoretical models. Scientists compared observed data with predictions from the Big Bang theory. This iterative process refined both the observations and the models. Data from different missions was often combined for a more comprehensive picture. By integrating results from COBE, WMAP, and Planck, scientists gained deeper insights. This combined approach enhanced the overall understanding of the CMB. Future missions continue to build on these methodologies. Advances in technology and techniques promise even more precise measurements. The ongoing refinement of these methods drives progress in cosmology. The rigorous methodology behind the discovery of the CMB exemplifies scientific inquiry. Careful planning, execution, and analysis were key to these groundbreaking findings. This meticulous approach continues to inform current and future research in astrophysics. The discovery of the cosmic microwave background was met with great excitement. It provided strong evidence for the Big Bang theory. Many scientists saw it as a pivotal moment in cosmology. Arno Penzias and Robert Wilson's findings quickly gained recognition. Their work was published in a prominent scientific journal. This sparked widespread interest and further research. Some scientists were initially skeptical. They questioned whether the detected radiation could be from another source. However, repeated observations confirmed its cosmic origin. The confirmation of the CMB was a major triumph. It validated theoretical predictions made decades earlier. This boosted confidence in the Big Bang model. Researchers across the globe began studying the CMB. They aimed to understand its implications for the universe's history. This led to a surge in cosmological research. The Nobel Prize awarded to Penzias and Wilson highlighted the significance of their discovery. It brought widespread recognition to their work. This honor underscored the importance of the CMB in astrophysics. Theoretical physicists were particularly intrigued. They saw the CMB as a window into the early universe. It provided a way to test their models and theories. The discovery also sparked new questions. Scientists wondered about the details of the early universe. They sought to understand the processes that led to the observed CMB patterns. Collaboration between observational and theoretical scientists increased. They worked together to interpret the CMB data. This interdisciplinary approach advanced the field significantly. The CMB's discovery also influenced other areas of physics. It impacted studies of dark matter and dark energy. These fields gained new insights from CMB research. Initial skepticism turned into widespread acceptance. As more data was collected, the evidence became undeniable. The CMB became a cornerstone of modern cosmology. Conferences and workshops were organized to discuss the findings. Scientists shared results and ideas. These gatherings helped to refine the understanding of the CMB. The discovery also inspired new generations of scientists. Many were drawn to the field by the excitement of these findings. The CMB's impact on science education was profound. Early reactions set the stage for future research. The scientific community's response was overwhelmingly positive. This enthusiasm continues to drive CMB studies today. The legacy of the initial discovery remains strong. It marked the beginning of a new era in cosmology. The scientific community's early reactions were just the start of a long journey of exploration and discovery. The cosmic microwave background, or CMB, is the afterglow of the Big Bang. It's a faint radiation that fills the entire universe. This radiation is a remnant from when the universe was just 380,000 years old. The significance of the CMB lies in its uniformity and slight fluctuations. These tiny variations represent the seeds of all current structures in the universe. They provide clues about the early conditions of the cosmos. The CMB is crucial for understanding the universe's history. It acts as a snapshot of the early universe. This snapshot helps scientists reconstruct events from the Big Bang to the present day. The CMB's uniform temperature supports the Big Bang theory. It indicates that the universe was once in a hot, dense state. As the universe expanded, this radiation cooled and stretched to microwave wavelengths. Temperature fluctuations in the CMB are essential for studying cosmic evolution. They show how matter was distributed in the early universe. These distributions eventually led to the formation of galaxies and other structures. The CMB also provides information about the universe's composition. It helps determine the proportions of dark matter, dark energy, and normal matter. These measurements are key for understanding the universe's overall makeup. Analyzing the CMB's fluctuations reveals the universe's age. Current estimates place it at around 13.8 billion years old. This precise age helps refine models of cosmic evolution. The CMB's power spectrum is a tool for studying its fluctuations. Peaks in this spectrum correspond to different physical processes in the early universe. This detailed analysis enhances our understanding of the cosmos. Polarization patterns in the CMB offer additional insights. These patterns result from scattering processes in the early universe. They help test theories about cosmic inflation and other fundamental physics. The CMB also informs us about the universe's geometry. By studying its patterns, scientists infer whether the universe is flat, open, or closed. Current data suggests that the universe is remarkably flat. The significance of the CMB extends to studying dark matter and dark energy. It provides indirect evidence for these mysterious components. This helps scientists piece together the full picture of the universe's composition. Observing the CMB requires precise instruments and methods. Satellites like COBE, WMAP, and Planck have been instrumental. Their detailed maps of the CMB are invaluable for cosmological research. The CMB also has practical applications. It helps calibrate instruments used in other astronomical observations. This ensures the accuracy and reliability of various measurements in astrophysics. The discovery and study of the CMB have revolutionized cosmology. They have provided a wealth of information about the universe's origins and evolution. This has led to numerous breakthroughs in understanding the cosmos. The CMB continues to be a rich field of research. Ongoing studies and future missions promise to reveal even more. The significance of the CMB in astrophysics remains profound and enduring. Measuring the cosmic microwave background involves highly sensitive instruments. These instruments detect microwave radiation from space. Precision is key to capturing the faint signals of the CMB. Satellites like COBE, WMAP, and Planck have been crucial for these measurements. They orbit far from Earth to avoid interference. This allows them to collect clearer data. COBE, the Cosmic Background Explorer, was the first satellite dedicated to studying the CMB. Launched in 1989, it provided the first detailed measurements. COBE's instruments included a differential microwave radiometer. The differential microwave radiometer compared temperatures from different parts of the sky. This method helped identify the small temperature variations. These variations are essential for understanding the early universe. Following COBE, the Wilkinson Microwave Anisotropy Probe, or WMAP, was launched in 2001. WMAP provided even more precise measurements of the CMB. It used a set of radiometers to scan the sky. WMAP's radiometers measured temperature differences with high accuracy. The satellite orbited the second Lagrange point, offering a stable environment. This stability improved the quality of the data. The Planck satellite, launched by the European Space Agency, took CMB measurements to new heights. Planck carried two main instruments, the low-frequency instrument and the high-frequency instrument. These covered a wide range of frequencies. Planck's instruments were cooled to near absolute zero. This reduced noise from the instruments themselves. Such low temperatures are vital for detecting the faint CMB signals. Ground-based observatories also contribute to measuring the CMB. The Atacama Cosmology Telescope and the South Pole Telescope are examples. These telescopes operate at high altitudes to minimize atmospheric interference. High-altitude balloons have been used as well. Experiments like Boomerang and Arcade flew balloons with CMB detectors. These missions provided valuable data, complementing satellite observations. The instruments measure the intensity of microwave radiation. They map this intensity across the sky. These maps reveal the tiny temperature fluctuations in the CMB. Calibration is crucial for ensuring accurate measurements. Instruments are calibrated using known reference sources. This process corrects for any potential errors or biases. Data processing involves removing foreground emissions. These emissions come from sources like our galaxy. Advanced algorithms help separate the CMB signal from these foregrounds. Combining data from different instruments improves accuracy. Each instrument has its strengths and limitations. By integrating their data, scientists obtain a more complete picture of the CMB. Continuous advancements in technology enhance our ability to measure the CMB. Future missions promise even greater precision. These improvements will deepen our understanding of the early universe. Anisotropies in the cosmic microwave background are slight variations in temperature. These variations are incredibly small, about 1 part in 100,000. They provide critical information about the early universe. These anisotropies are essential for understanding the universe's structure. They represent the density fluctuations that eventually formed galaxies and clusters. By studying them, scientists can trace the evolution of cosmic structures. The anisotropies were first detected by the COBE satellite. COBE's measurements showed that the CMB is not perfectly uniform. This discovery was a major breakthrough in cosmology. WMAP provided a more detailed view of these anisotropies. Its high-resolution data revealed finer details in the temperature fluctuations. This helped refine models of the universe's formation and evolution. Planck further improved our understanding of anisotropies. With its advanced instruments, Planck mapped the CMB with unprecedented precision. This detailed map has been invaluable for cosmological studies. The patterns of anisotropies are not random. They follow a specific statistical distribution. This distribution matches predictions from the theory of cosmic inflation. Cosmic inflation theory suggests a rapid expansion of the universe just after the Big Bang. This expansion would have stretched and smoothed out any initial irregularities. The anisotropies we observe are imprints of quantum fluctuations from that time. The anisotropies also provide information about the universe's composition. They help determine the proportions of dark matter, dark energy, and normal matter. This is crucial for understanding the overall makeup of the cosmos. Analyzing anisotropies involves studying the CMB's power spectrum. The power spectrum shows how temperature variations vary with scale. Peaks in this spectrum correspond to different physical processes in the early universe. The first peak in the power spectrum reflects sound waves in the early universe. These sound waves were caused by the interaction of matter and radiation. Their characteristics provide clues about the universe's density and expansion rate. Subsequent peaks give insights into the properties of dark matter and dark energy. They help refine our understanding of these mysterious components. This information is vital for constructing accurate cosmological models. The study of anisotropies also tests the isotropy of the universe. Isotropy means the universe looks the same in all directions. While generally true, slight deviations are key to understanding cosmic evolution. Anomalies in anisotropies, like the axis of evil, challenge existing theories. These anomalies suggest there may be unknown factors influencing the CMB. Ongoing research aims to explain these intriguing features. Anisotropies also have practical applications. They help calibrate astronomical instruments and validate theoretical models. Their study is integral to both observational and theoretical cosmology. Understanding anisotropies continues to be a dynamic field of research. Each new observation brings us closer to unraveling the mysteries of the early universe. The insights gained from studying these temperature fluctuations are profound. Theoretical predictions of the cosmic microwave background date back to the 1940s. Scientists like George Gamow and his colleagues predicted a residual heat from the Big Bang. This heat, they theorized, would be detectable as a faint glow. Their calculations suggested that this radiation would be in the microwave range. They predicted it would have a nearly uniform temperature. This background radiation would be a crucial piece of evidence for the Big Bang theory. In the 1960s, further theoretical work refined these predictions. Physicists predicted not just the existence of the CMB, but its specific properties. They calculated the temperature and spectrum of this background radiation. These early predictions estimated the CMB temperature to be around a few degrees above absolute zero. This estimate was remarkably close to the actual measured value. The accuracy of these predictions validated the theoretical models. The theory also predicted slight anisotropies in the CMB. These small temperature fluctuations would arise from density variations in the early universe. These fluctuations would eventually lead to the formation of galaxies and other structures. Cosmic inflation theory, developed in the 1980s, provided more detailed predictions. Inflation posited a rapid expansion of the universe shortly after the Big Bang. This expansion would leave distinct imprints on the CMB. Inflation theory predicted a specific pattern in the CMB's anisotropies. It suggested a Gaussian, random distribution of these fluctuations. This pattern was later confirmed by observations. The power spectrum of the CMB was another key prediction. Theoretical models predicted specific peaks in this spectrum. These peaks correspond to different scales of density fluctuations. The first peak in the power spectrum was expected to reflect the size of the universe's horizon at the time of recombination. Subsequent peaks would provide information about the universe's density and composition. These predictions have been confirmed by data from COBE, WMAP, and Planck. The polarization of the CMB was also predicted by theoretical models. Polarization patterns would arise from scattering processes in the early universe. These patterns offer additional tests for inflationary theories. The Sachs-Wolf effect is another theoretical prediction. It describes how gravitational redshift affects the CMB photons. This effect provides insights into the large-scale structure of the universe. The integrated Sachs-Wolf effect extends this concept. It considers how evolving gravitational potentials affect the CMB. This effect is sensitive to the presence of dark energy. The Sunyaev-Zeldovich effect was predicted as well. It describes how CMB photons interact with hot gas in galaxy clusters. This effect provides valuable information about the distribution of matter. Theoretical predictions have been crucial in guiding observations. They have helped design experiments and interpret data. The close agreement between theory and observation has strengthened the Big Bang model. The study of the CMB continues to test these predictions. Each new observation challenges and refines our theoretical understanding. The interplay between theory and observation drives progress in cosmology. The cosmic microwave background plays a crucial role in cosmology. It serves as a snapshot of the universe when it was just 380,000 years old. This provides a direct link to the conditions of the early universe. The CMB helps us understand the Big Bang theory. Its uniform temperature across the sky supports the idea of a hot, dense origin. This evidence is a cornerstone of modern cosmological models. Temperature fluctuations in the CMB are key to studying the universe's structure. These tiny variations represent the initial density differences. Over time, these differences led to the formation of galaxies and clusters. The CMB allows us to measure the universe's age with high precision. By analyzing its properties, scientists have determined that the universe is approximately 13.8 billion years old. This measurement is one of the most accurate in cosmology. Cosmologists use the CMB to study the composition of the universe. It helps determine the proportions of dark matter, dark energy, and normal matter. These insights are crucial for understanding the overall makeup of the cosmos. The CMB's power spectrum reveals details about the early universe. Peaks in this spectrum correspond to sound waves from that time. These peaks provide information about the universe's density and expansion rate. Polarization patterns in the CMB offer additional clues. They result from scattering processes in the early universe. These patterns help test theories about cosmic inflation and other fundamental physics. The CMB also provides evidence for the universe's isotropy. Isotropy means the universe looks the same in all directions. The CMB's uniformity supports this principle on large scales. Anomalies in the CMB, like the axis of evil, challenge our understanding. These anomalies suggest there may be unknown factors at play. Ongoing research aims to explain these intriguing features. The CMB's study informs models of dark matter and dark energy. It provides indirect evidence for these mysterious components. This helps scientists build comprehensive cosmological models. The CMB's role extends to calibrating astronomical instruments. Accurate measurements of the CMB help ensure other observations are reliable. This makes it a valuable reference point in astrophysics. The discovery of the CMB revolutionized cosmology. It provided strong evidence for the Big Bang theory and reshaped our understanding of the universe. Its importance in cosmological research cannot be overstated. The CMB continues to drive advancements in the field. Each new mission and observation adds to our knowledge. This ongoing research deepens our understanding of the cosmos. The interplay between CMB data and theoretical models is vital. It helps refine our understanding of the universe's origins and evolution. This dynamic relationship drives progress in cosmology. The study of the CMB remains a vibrant and evolving area. Future missions promise even greater insights. The CMB's role in cosmology will continue to be central for years to come. Anomalies in the cosmic microwave background are deviations from the expected uniformity. These anomalies challenge our current cosmological models. They suggest that there might be unknown factors influencing the CMB. One of the most notable anomalies is the axis of evil. This refers to an unexpected alignment of temperature fluctuations. Its discovery has sparked significant debate among scientists. The cold spot is another prominent anomaly. This region of the CMB is unusually cold compared to its surroundings. It raises questions about the uniformity of the early universe. Some anomalies might be due to foreground contamination. Galactic emissions or cosmic dust can affect CMB measurements. Scientists work to separate these effects from the true cosmic signal. Instrumental errors are another possible source of anomalies. Calibration issues or data processing errors can introduce artifacts. Ensuring accuracy in measurements is crucial for reliable data. Statistical flukes are considered when evaluating anomalies. Given the vast amount of data, some unexpected patterns may occur by chance. Distinguishing these from significant anomalies is a challenge. The integrated Sachs-Wolf effect might explain some anomalies. This effect involves changes in gravitational potential over time. It can create temperature fluctuations in the CMB. The Sunyaev-Zeldovich effect also plays a role. This effect occurs when CMB photons interact with hot gas in galaxy clusters. It can introduce distortions in the CMB data. Topological defects from the early universe could cause anomalies. These include cosmic strings or domain walls. They could leave imprints on the CMB that deviate from standard predictions. Some theories suggest that large-scale structures influence anomalies. The distribution of galaxies and clusters might affect CMB patterns. This interaction is a subject of ongoing research. Multiverse theories propose another explanation. They suggest our universe might be one of many. Interactions with other universes could create anomalies in the CMB. Quantum effects in the early universe might contribute to anomalies. These effects could introduce fluctuations beyond standard models. Understanding these contributions requires advanced theoretical work. Modifications to the inflationary model are also considered. Alternative inflation scenarios might predict different CMB patterns. Exploring these models helps explain observed anomalies. Cosmologists continue to investigate these anomalies with new data. Upcoming missions and advanced instruments provide better measurements. This research aims to clarify the nature and cause of these anomalies. Understanding CMB anomalies is crucial for refining cosmological theories. They offer clues about the early universe and its underlying physics. This ongoing investigation is vital for advancing our knowledge of the cosmos. The cosmic microwave background exhibits several types of anomalies. These anomalies are deviations from the expected uniform patterns. Each type provides unique challenges and insights for cosmologists. One well-known anomaly is the axis of evil. This refers to an unusual alignment of temperature fluctuations along a specific axis. Its discovery has led to extensive debates in the scientific community. The cold spot is another significant anomaly. It's an unusually large, cool region in the CMB. This area is much colder than the surrounding regions and has puzzled scientists since its discovery. There's also the dipole anomaly. This involves a larger than expected variation between the hot and cold spots. It raises questions about the overall isotropy of the universe. Non-Gaussianity is another type of anomaly. Standard models predict a Gaussian distribution of temperature fluctuations. Deviations from this pattern suggest new physics or unknown processes in the early universe. The quadrupole and octupole alignments are specific forms of anisotropies. These involve the alignment of low-order multipoles in the CMB. They challenge the principle of isotropy on large scales. The hemispherical power asymmetry is an observed difference in power between two halves of the sky. This asymmetry suggests that one side of the universe is slightly different from the other. It contradicts the expectation of uniformity. Large-scale anomalies also include the north-south asymmetry. This refers to differences in the CMB signal between the northern and southern celestial hemispheres. It poses questions about the large-scale structure of the universe. Localized anomalies like the Eridanus supervoid are also noteworthy. This vast region of space appears to contain fewer galaxies than expected. Such voids can affect the CMB and contribute to anomalies like the cold spot. The low L anomaly involves unexpected patterns in the lowest multipole moments of the CMB. These moments correspond to the largest scales in the universe. Their unexpected behavior suggests new physical phenomena. Foreground anomalies result from interference by local sources. Emissions from our galaxy or interstellar dust can distort the CMB signal. Separating these effects from the true cosmic background is a complex task. Instrumental anomalies arise from the limitations of measurement tools. Calibration errors or data processing artifacts can create false patterns. Ensuring accurate and reliable measurements is crucial for identifying true anomalies. Gravitational lensing anomalies occur when massive objects distort the CMB. This effect can create arcs or other features in the data. Understanding these distortions helps refine cosmological models. Cosmic string imprints are hypothetical anomalies. If cosmic strings exist, they could leave distinctive marks on the CMB. Searching for these signatures tests theories about the early universe. Investigating these anomalies involves detailed analysis and advanced simulations. Each anomaly provides a potential clue about the universe's fundamental nature. Ongoing research aims to understand and explain these intriguing features. The significance of these anomalies lies in their potential to challenge existing cosmological models. They suggest that our understanding of the universe might be incomplete. Each anomaly offers a clue that could lead to new physics. The axis of evil, for instance, questions the principle of isotropy. If the universe has a preferred direction, it could imply new physics. This anomaly has led to various hypotheses and further investigations. The cold spot's significance lies in its size and temperature. Such a large cold region is difficult to explain with standard models. It raises the possibility of unusual large-scale structures or even other universes. Dipole anomalies highlight the need to reassess our assumptions. Larger than expected variations between hot and cold spots could indicate underlying factors. These anomalies drive scientists to refine their models. Non-Gaussianity would suggest new physics in the early universe. Deviations from the Gaussian distribution imply different processes at work. This could lead to breakthroughs in our understanding of cosmic inflation. Quadrupole and octupole alignments challenge large-scale uniformity. If these alignments are real, they could point to new cosmic phenomena. Their study is essential for testing the limits of current theories. Hemispherical power asymmetry suggests a directional bias. This asymmetry implies that different regions of the universe evolved differently. Understanding it could reveal new aspects of cosmic evolution. North-south asymmetry also questions uniformity. Differences between the celestial hemispheres indicate possible large-scale anomalies. This asymmetry drives further exploration of the universe's structure. Localized anomalies like the Eridanus supervoid hint at vast cosmic structures. These voids could influence the CMB in unexpected ways. Studying them helps map the large-scale distribution of matter. The low-L anomaly challenges our understanding of large-scale fluctuations. Unexpected patterns in the lowest multipole moments suggest unknown influences. This anomaly requires more detailed theoretical work. Foreground anomalies remind us of the complexity of CMB measurements. Galactic emissions and interstellar dust must be carefully accounted for. Properly addressing these helps isolate true cosmic signals. Instrumental anomalies highlight the importance of precision. Ensuring accurate measurements is crucial for reliable data. Instrumental issues must be resolved to validate true CMB features. Gravitational lensing anomalies show how massive objects influence the CMB. These distortions can provide insights into the distribution of matter. Understanding lensing effects refines cosmological models. Cosmic string imprints, if found, would confirm new aspects of early universe physics. These hypothetical anomalies test theories about cosmic strings. Finding such imprints would be a significant breakthrough. Overall, these anomalies are essential for advancing cosmology. They push the boundaries of our knowledge and prompt new theories. Investigating them deepens our understanding of the universe. Detecting anomalies in the cosmic microwave background involves precise measurements. Scientists use advanced satellites and telescopes to collect data. These instruments are designed to capture the faint microwave radiation from space. Satellites like COBE, WMAP, and Planck have been crucial in detecting anomalies. They orbit the Earth far from atmospheric interference. This allows them to obtain clearer and more accurate data. Ground-based observatories also play a role. Telescopes like the Atacama Cosmology Telescope and the South Pole Telescope provide complementary observations. Their high-altitude locations reduce atmospheric distortion. Data collection begins with mapping the CMB across the sky. Instruments scan the sky multiple times to ensure coverage. This repeated scanning helps identify consistent patterns. Once data is collected, it undergoes rigorous calibration. Calibration ensures that the measurements are accurate and free from instrumental biases. This process is vital for reliable anomaly detection. Scientists then process the data to remove foreground emissions. Emissions from our galaxy and other sources can contaminate the CMB signal. Advanced algorithms separate these foregrounds from the true cosmic background. Temperature maps are created from the processed data. These maps show the tiny fluctuations in the CMB's temperature. Anomalies appear as deviations from the expected uniform pattern. Analyzing the power spectrum is another crucial step. The power spectrum reveals how temperature fluctuations vary with scale. Anomalies often appear as unexpected peaks or patterns in this spectrum. Statistical analysis helps distinguish genuine anomalies from random fluctuations. Scientists use statistical tools to evaluate the significance of observed patterns. This helps determine whether an anomaly is real or a statistical artifact. Cross-checking with theoretical models is essential. Observed anomalies are compared with predictions from cosmological models. Discrepancies can indicate new physics or errors in existing theories. Gravitational lensing effects are also considered. Massive objects can distort the CMB, creating anomalies. Identifying these lensing effects requires careful analysis of the data. Polarization measurements provide additional insights. Polarization patterns can reveal subtle anomalies not visible in temperature maps. These patterns help test theories about the early universe. Advanced simulations play a role in detecting anomalies. Simulations recreate the CMB under various conditions. Comparing real data with simulations helps identify unexpected features. Collaborative efforts enhance anomaly detection. Scientists worldwide share data and techniques. This collaboration ensures comprehensive analysis and validation. Future missions promise even more precise measurements. Upcoming satellites and improved instruments will provide better data. These advancements will help detect and understand anomalies more accurately. Detecting anomalies is an ongoing process. Each new observation and analysis brings fresh insights. This continuous effort is crucial for unraveling the mysteries of the cosmos. Possible explanations for anomalies in the cosmic microwave background range from mundane to groundbreaking. Some scientists suggest that foreground contamination could account for certain anomalies. Galactic emissions or cosmic dust might distort the CMB signal. Instrumental errors are another straightforward explanation. Calibration issues or data processing mistakes could introduce false patterns. Ensuring precision in measurements is crucial to ruling out this possibility. Statistical flukes are also considered. Given the vast amount of data, some unexpected patterns might occur by chance. Distinguishing these from true anomalies requires rigorous statistical analysis. The integrated Sachs-Wolf effect could explain some anomalies. This effect involves changes in gravitational potential over time, which can create temperature fluctuations. It's especially relevant in a universe dominated by dark energy. The Sunyaev-Zeldovich effect is another possibility. This occurs when CMB photons interact with hot gas in galaxy clusters, distorting the CMB data. Understanding these interactions helps in identifying and correcting such distortions. Topological defects from the early universe, like cosmic strings or domain walls, might leave imprints on the CMB. If these defects exist, they could create distinctive patterns that deviate from standard predictions. Their detection would support new physics beyond the standard model. Large-scale structures in the universe might influence the CMB. The distribution of galaxies and clusters could affect the patterns we observe. This interaction between large-scale structures and the CMB is a subject of ongoing research. Multiverse theories propose a more exotic explanation. These theories suggest our universe might be one of many, and interactions with other universes could create anomalies in the CMB. This hypothesis, while speculative, opens intriguing possibilities. Quantum effects in the early universe might also contribute to anomalies. These effects could introduce fluctuations beyond what standard models predict. Exploring these quantum influences requires advanced theoretical work. Alternative inflationary models are another area of interest. Different scenarios of cosmic inflation might predict different patterns in the CMB. Investigating these models can help explain observed anomalies. Modified gravity theories might offer explanations as well. These theories propose changes to our understanding of gravity, which could affect CMB patterns. Testing these theories against observational data is crucial for their validation. Exotic particles or new forms of matter might also be at play. The existence of unknown particles could influence the early universe's conditions, leading to anomalies. Identifying such particles would revolutionize our understanding of physics. Some anomalies could be remnants of the initial conditions of the universe. If the universe began with certain asymmetries, these might still be visible in the CMB. This idea links the present universe to its earliest moments. Dark matter interactions might also explain some anomalies. If dark matter behaves differently than expected, it could affect the CMB. Studying these interactions helps refine dark matter theories. Finally, ongoing observations and future missions will provide more data. As our measurement techniques improve, we'll gain a clearer picture of these anomalies. This continuous research is essential for advancing cosmology. The alignment of the multipoles in the cosmic microwave background is one of the most intriguing anomalies. Multipoles are mathematical representations of the CMB's temperature fluctuations on different scales. The lowest multipoles, like the quadrupole and octupole, show unexpected alignments. These alignments suggest a preferred direction in the universe, which contradicts the cosmological principle of isotropy. The principle of isotropy states that the universe should look the same in all directions. The observed alignment challenges this foundational assumption. Researchers first noticed the alignment in data from the WMAP satellite. The quadrupole and octupole moments were unexpectedly aligned along a specific axis. This phenomenon has been dubbed the axis of evil. The axis of evil has been a subject of intense debate and scrutiny. Some scientists believe it may be a statistical fluke. Others argue it points to new physics or previously unknown cosmic phenomena. Instrumental errors have been considered as a possible cause. Calibration issues or systematic biases in the data could create such alignments. However, subsequent analyses have aimed to rule out these errors. Foreground contamination is another potential explanation. Galactic emissions or interstellar dust could affect the observed CMB patterns. Advanced data processing techniques attempt to separate these effects from the true cosmic signal. If the alignment is real, it could imply new physics. It might suggest that the universe has a preferred direction, challenging our understanding of cosmological symmetry. This possibility has profound implications for theoretical models. Some theories propose that the alignment could be due to large-scale cosmic structures. Massive structures like supervoids or superclusters might influence the CMB on large scales. This interaction could create the observed alignment. Cosmic inflation models have been modified to account for such alignments. Some alternative inflationary scenarios predict deviations from perfect isotropy. These models are being tested against observational data. Quantum effects in the early universe might also play a role. Quantum fluctuations during inflation could introduce anisotropies. These fluctuations might leave imprints on the CMB that align in unexpected ways. Multiverse theories offer another speculative explanation. If our universe is one of many, interactions with other universes could affect the CMB. Such interactions might create alignments like those observed. Gravitational waves from the early universe are also considered. These waves could influence the CMB's multipole moments. Detecting such gravitational waves would provide new insights into the universe's infancy. Ongoing observations aim to clarify the nature of the alignment. Future missions with improved sensitivity and resolution will provide better data. These observations are crucial for understanding the alignment's origin. Theoretical work continues to explore all possible explanations. Researchers are developing new models and refining existing ones. This theoretical effort is essential for interpreting the observational data. Understanding the alignment of the multipoles is a key goal in cosmology. It has the potential to reveal new aspects of the universe and its underlying physics. This anomaly continues to drive both observational and theoretical research. Statistical significance is crucial in evaluating anomalies in the cosmic microwave background. It helps determine whether observed patterns are genuine or just random fluctuations. For the alignment of the multipoles, assessing statistical significance is key. Scientists use various statistical tools to analyze CMB data. These tools help quantify the likelihood that an anomaly is real. They compare the observed data with predictions from cosmological models. For the axis of evil, researchers calculate the probability of such an alignment occurring by chance. Initial studies suggested that the alignment is highly unlikely to be a random event. This low probability indicates potential significance. To strengthen these findings, scientists perform Monte Carlo simulations. These simulations generate many random CMB maps to compare with actual observations. The results help assess the anomaly's significance more robustly. Statistical significance is often reported as a p-value. A low p-value indicates that the observed pattern is unlikely to occur by chance. For the axis of evil, the p-value has been found to be quite low, suggesting it is not a fluke. However, statistical significance alone is not conclusive. It must be supported by thorough analysis and cross-checking. Researchers also consider potential sources of error and alternative explanations. Different datasets are used to verify statistical significance. Comparing results from WMAP and Planck, for example, helps ensure consistency. Consistent findings across datasets reinforce the anomaly's significance. Foreground contamination and instrumental effects are rigorously tested. These factors can introduce biases that affect statistical results. Eliminating such biases is crucial for accurate significance assessment. Cross-validation with independent methods strengthens the findings. For example, using different statistical techniques or data subsets. This approach helps confirm that the anomaly is not an artifact of a specific method. Despite strong statistical evidence, some researchers remain cautious. They argue for more data and refined models to fully understand the anomaly. This caution is essential for scientific rigor. Statistical significance must be interpreted in context. It indicates the likelihood of an anomaly, but does not explain its cause. Understanding the underlying physics requires further investigation. Ongoing research aims to refine statistical methods. Improved techniques provide more accurate assessments of significance. This continuous improvement is vital for advancing cosmological studies. Future observations will enhance statistical analysis. New missions with better sensitivity and resolution will provide richer data. These observations are expected to clarify the significance of various anomalies. Statistical significance guides the direction of theoretical work. Significant anomalies prompt the development of new models and theories. This interplay between observation and theory drives scientific progress. Ultimately, the goal is to understand what the statistical significance reveals about the universe. It provides a pathway to deeper insights into the cosmos and its fundamental properties. This quest continues to inspire and challenge cosmologists. Geometric peculiarities in the cosmic microwave background are another intriguing aspect of the anomalies. These peculiarities refer to unexpected shapes and alignments in the temperature fluctuations. Understanding them could reveal new physics about the universe. One example is the alignment of the quadrupole and octupolar moments. These moments are expected to be randomly oriented, but they show a surprising alignment along a particular axis. This alignment challenges our understanding of the universe's geometry. Another geometric peculiarity is the planar nature of some multipoles. Instead of being spherically distributed, they appear to lie on a plane. This flatness is not predicted by standard cosmological models. The cold spot also exhibits geometric oddities. Its shape and size are unusual, making it stand out from other temperature fluctuations. This peculiarity has led to various hypotheses about its origin. Researchers have explored whether these geometric features could result from cosmic topology. If the universe has a non-trivial shape, it could create patterns in the CMB. For instance, a toroidal or saddle-shaped universe might produce specific alignments. Another idea is that these geometric peculiarities result from large-scale structures. Massive objects or voids in the universe could distort the CMB. This distortion might create the observed planar features. Some theories suggest that primordial gravitational waves could influence the CMB's geometry. These waves, generated in the early universe, could leave imprints on the CMB. Detecting such imprints would provide insights into the universe's infancy. Geometric peculiarities are also examined through the lens of modified gravity theories. These theories propose changes to general relativity that could affect the CMB. Understanding how modified gravity influences CMB geometry is an active area of research. Quantum effects in the early universe might also create geometric anomalies. Fluctuations at quantum scales could leave large-scale imprints. These effects challenge our understanding of quantum mechanics and cosmology. The role of dark energy in shaping the CMB's geometry is another consideration. Dark energy influences the universe's expansion and could affect the CMB. Studying this connection helps refine models of cosmic acceleration. Foreground effects must be carefully considered. Emissions from our galaxy or other sources could mimic geometric anomalies. Advanced data processing techniques aim to separate these foregrounds from true cosmic signals. Instrumental artifacts could also contribute to observed geometric peculiarities. Calibration errors or systematic biases might introduce false patterns. Ensuring accurate measurements is crucial for reliable interpretation. Cross-checking with different observational datasets helps validate geometric features. Consistency across data from various missions strengthens the findings. This approach helps rule out artifacts and confirms true anomalies. Geometric peculiarities inspire new theoretical models. These models aim to explain the unexpected shapes and alignments. Testing these theories against observational data drives progress in cosmology. Future missions with enhanced capabilities will provide better data on geometric peculiarities. Higher resolution and sensitivity will clarify these features. Continued observation and analysis are essential for understanding the universe's geometric nature. Temperature fluctuations in the cosmic microwave background are tiny variations in temperature across the sky. These fluctuations are about 1 part in 100,000, yet they hold significant information about the universe's early conditions. They represent slight differences in density from the time when the CMB was emitted. These variations are critical for understanding the formation of large-scale structures. The denser regions in the early universe eventually grew into galaxies and clusters. By studying these fluctuations, scientists can trace the history of cosmic structure formation. The power spectrum of the CMB is a key tool for analyzing these fluctuations. It shows how the temperature variations are distributed across different scales. Peaks in the power spectrum correspond to specific physical processes in the early universe. The first peak in the power spectrum is particularly important. It represents sound waves in the primordial plasma, providing information about the universe's density and composition. Subsequent peaks give insights into the proportions of dark matter and dark energy. Temperature fluctuations also reveal information about the universe's geometry. The overall shape of the power spectrum helps determine whether the universe is flat, open, or closed. Current data suggests the universe is remarkably flat. Analyzing these fluctuations involves advanced statistical techniques. Scientists compare the observed data with predictions from various cosmological models. This comparison helps refine our understanding of the universe's fundamental properties. Polarization patterns in the CMB complement temperature data. These patterns arise from the scattering of CMB photons by electrons. They provide additional information about the early universe, especially regarding cosmic inflation. Temperature fluctuations are influenced by gravitational lensing. Massive objects like galaxy clusters can distort the CMB, altering its temperature patterns. Studying these distortions helps map the distribution of matter in the universe. Foreground emissions must be carefully subtracted to accurately measure CMB fluctuations. Galactic dust and other sources can contaminate the signal. Advanced algorithms are used to clean the data, isolating the true cosmic background. Instrumental precision is crucial for detecting these tiny variations. Satellites like COBE, WMAP, and Planck have been designed to measure the CMB with high accuracy. Each mission has improved our ability to map these fluctuations. Temperature fluctuations provide a test for theories of the early universe. Different models of cosmic inflation predict specific patterns in the CMB. Observing these patterns helps validate or challenge these theories. The tiny variations also offer clues about dark matter. The way these fluctuations evolve over time can reveal the properties of dark matter particles. This information is vital for understanding the nature of this mysterious substance. Researchers use computer simulations to model temperature fluctuations. These simulations recreate the conditions of the early universe, predicting the CMB's appearance. Comparing these predictions with actual data helps refine cosmological models. Temperature fluctuations are also connected to the integrated Sachs-Wolf effect. This effect occurs when CMB photons pass through varying gravitational potentials. It provides insights into the influence of dark energy on the universe's expansion. Future missions will continue to study these fluctuations in even greater detail. Improved technology will provide higher resolution and sensitivity, revealing new aspects of the CMB. These studies will deepen our understanding of the universe's origins and evolution. Polarization patterns in the cosmic microwave background provide additional insights into the early universe. These patterns arise from the scattering of CMB photons by electrons shortly after the Big Bang. They carry information about the conditions and processes that occurred during that time. There are two types of polarization patterns, E modes and B modes. E modes are simpler and have been detected with high precision. They are primarily generated by density fluctuations in the early universe. B modes are more complex and harder to detect. They can be produced by gravitational waves from cosmic inflation. Detecting B modes would provide strong evidence for inflation and insights into the universe's rapid expansion. E-mode polarization helps refine measurements of the CMB temperature fluctuations. These patterns allow scientists to separate the different sources of temperature variations. This separation improves the accuracy of cosmological parameters. The study of B modes is particularly exciting. If detected, B modes could reveal the presence of primordial gravitational waves. These waves are ripples in spacetime, caused by rapid inflation in the early universe. Polarization patterns also provide information about the revolutionization epoch. This period occurred several 100 million years after the Big Bang, when the first stars and galaxies formed. Polarization data helps understand how reionization progressed. The Planck satellite has made significant contributions to measuring polarization. Its high sensitivity and resolution have produced detailed maps of E-mode polarization. These maps enhance our understanding of the universe's history. Ground-based experiments like BICEP-2 and the South Pole Telescope focus on detecting B modes. These experiments operate in extremely cold and dry environments to reduce noise. Their goal is to find the faint B mode signal amidst other sources of radiation. Analyzing polarization patterns involves advanced techniques. Scientists use statistical methods to extract polarization data from the overall CMB signal. This analysis is crucial for interpreting the information contained in the CMB. Theoretical models predict specific polarization patterns. By comparing observed patterns with predictions, researchers can test these models. This comparison helps refine theories about cosmic inflation and other early universe phenomena. Polarization patterns also interact with gravitational lensing. Lensing by large-scale structures can distort the polarization signal. Studying these distortions helps map the distribution of matter in the universe. Foreground emissions can contaminate polarization measurements. Galactic dust and other sources emit polarized light that can interfere with CMB data. Advanced data processing techniques aim to remove these contaminants. The precision of polarization measurements continues to improve. Future missions with enhanced capabilities will provide even more detailed data. These advancements will help resolve outstanding questions about the early universe. Polarization patterns add a new dimension to CMB studies. They provide complementary information to temperature fluctuations. Together, these datasets offer a more complete picture of the universe's origins and evolution. Ongoing research into polarization patterns is vital. Each new discovery adds to our understanding of the cosmos. This field continues to be a dynamic and exciting area of cosmological research. The cosmic microwave background has had a profound impact on the standard model of cosmology. It has provided critical evidence supporting the Big Bang theory. The detailed measurements of the CMB have refined our understanding of the universe's origin and evolution. The standard model of cosmology, also known as the Lambda CDM model, incorporates the CMB data. This model describes a universe composed of dark energy, dark matter, and normal matter. The CMB helps determine the proportions of these components. Temperature fluctuations in the CMB have confirmed the presence of dark matter. These fluctuations indicate that dark matter played a significant role in the formation of large-scale structures. This insight is crucial for understanding galaxy and cluster formation. The CMB has also provided evidence for dark energy. The observed acceleration of the universe's expansion is consistent with the effects of dark energy. This mysterious force makes up about 70% of the universe's total energy density. The detailed maps of the CMB have refined measurements of the universe's age. Current estimates place the age at approximately 13.8 billion years. This precise age helps constrain models of cosmic evolution. The CMB data has also confirmed the flat geometry of the universe. Observations show that the universe is remarkably flat, supporting the inflationary model. This flatness implies that the universe's density is very close to the critical value. Polarization patterns in the CMB have provided additional support for inflation. E-mode polarization patterns align with predictions from inflationary theory. Detecting B-mode polarization would further confirm the inflationary model. The power spectrum of the CMB has revealed multiple acoustic peaks. These peaks correspond to sound waves in the early universe's plasma. Analyzing these peaks helps refine the values of cosmological parameters. The standard model of cosmology includes the concept of reionization. Polarization data from the CMB provides insights into this epoch, Understanding reionization helps explain the formation of the first stars and galaxies. Gravitational lensing effects observed in the CMB data have mapped the distribution of matter. This mapping helps understand the large-scale structure of the universe. It also provides insights into the nature and distribution of dark matter. The integrated Sachs-Wolf effect, seen in the CMB, supports the existence of dark energy. This effect results from changes in gravitational potential affecting CMB photons. It provides another piece of evidence for the accelerated expansion of the universe. The CMB has also influenced our understanding of neutrinos. Measurements suggest a specific number of light, weakly interacting particles. This information helps refine particle physics models. The CMB's role in testing modified gravity theories is significant. Observations help determine whether general relativity needs adjustments. These tests are crucial for understanding gravity on cosmic scales. Future missions will continue to refine the standard model of cosmology. Improved data will provide more precise measurements of cosmological parameters. This ongoing research is essential for deepening our understanding of the universe. The impact of the CMB on the standard model of cosmology cannot be overstated. It has provided critical evidence and refined our understanding of the universe's fundamental properties. The study of the CMB remains central to modern cosmology. Challenges to the isotropy assumption arise from various anomalies in the cosmic microwave background. Isotropy implies that the universe looks the same in all directions, but certain observations suggest otherwise. These challenges prompt a re-evaluation of fundamental cosmological principles. One significant challenge is the axis of evil. This unexpected alignment of temperature fluctuations suggests a preferred direction. It contradicts the expectation of uniformity on large scales. The cold spot is another anomaly that questions isotropy. Its unusual size and temperature deviation are difficult to explain with standard models. This raises the possibility of unknown physical processes at work. The hemispherical power asymmetry suggests that one half of the sky has different temperature fluctuations than the other. This asymmetry challenges the notion of a homogeneous universe. It indicates that there may be large-scale variations in the cosmic fabric. Dipolar, quadrupole, and octupole alignments also undermine isotropy. These low-order multipole moments should be randomly oriented, but they show surprising alignments. This pattern suggests underlying factors influencing the CMB. Foreground contamination could partially explain these challenges. Galactic emissions and interstellar dust might distort the CMB signal. However, advanced techniques aim to separate these effects from genuine cosmic features. Instrumental errors are another consideration. Calibration issues or biases in data collection could introduce false patterns. Ensuring precision in measurements is crucial to address this possibility. Statistical analysis helps determine the significance of observed anisotropies. Scientists assess whether these patterns could occur by chance. Consistent findings across different data sets strengthen the case for genuine anomalies. Large-scale structures might influence the CMB. The distribution of galaxies and clusters could create anisotropies. This interaction between matter and the CMB is an area of active research. Cosmic inflation models are being tested to explain these anomalies. Alternative inflation scenarios might predict deviations from perfect isotropy. These models are continually refined based on observational data. Quantum effects in the early universe could contribute to anisotropies. Fluctuations at quantum scales might leave large-scale imprints. Understanding these effects requires integrating quantum mechanics with cosmology. Modified gravity theories offer another explanation. Changes to our understanding of gravity could affect the CMB. Testing these theories against CMB data helps explore their validity. The possibility of a multiverse is also considered. Interactions with other universes might create anisotropies in our own. This speculative idea opens new avenues for theoretical exploration. Gravitational lensing by large-scale structures might distort the CMB. Massive objects bending light could create anisotropic patterns. Studying these effects helps map the distribution of matter. Ongoing observations aim to clarify the isotropy assumption. Future missions with improved sensitivity and resolution will provide better data. This research is essential for understanding the true nature of the universe. Addressing challenges to isotropy is crucial for refining cosmological models. These anomalies offer potential insights into new physics and the early universe. The study of isotropy and its deviations continues to drive progress in cosmology. The potential need for new physics arises from unexplained anomalies in the cosmic microwave background. These anomalies challenge existing cosmological models. They suggest that our current understanding might be incomplete. One possibility is that unknown particles influence the early universe. These particles could interact in ways not accounted for in the standard model. Detecting such particles would revolutionize our knowledge of fundamental physics. Modifications to the theory of gravity are also considered. General relativity may need adjustments to explain certain anomalies. These modifications could provide new insights into how gravity operates on cosmic scales. The concept of dark energy is another area where new physics might emerge. Dark energy drives the accelerated expansion of the universe, but its nature is still unknown. Anomalies in the CMB could offer clues about its properties. Quantum mechanics might hold answers as well. Integrating quantum theory with cosmology could explain early universe fluctuations. This integration requires new frameworks beyond current models. Multiverse theories propose that our universe is one of many. Interactions with other universes could create observable anomalies. This idea, while speculative, opens new possibilities for understanding cosmic phenomena. Cosmic inflation models might need refinement. Alternative inflation scenarios could account for deviations from isotropy. Exploring these scenarios helps test the limits of inflationary theory. The behavior of dark matter is another focus. Dark matter's interactions could create unexpected patterns in the CMB. Understanding these interactions is key to uncovering dark matter's true nature. Exotic forms of matter and energy might exist. These forms could affect the early universe in novel ways. Detecting their influence would provide groundbreaking insights. Topological defects from the early universe could explain some anomalies. Defects like cosmic strings might leave imprints on the CMB. Finding evidence of these defects would support new physics theories. String theory offers a potential framework for these new ideas. It attempts to unify gravity with other fundamental forces. Observing string theory's predictions in the CMB would be a major breakthrough. Modified gravity theories like MOND or Multiverse are also explored. These theories propose changes to Newtonian dynamics and general relativity. Testing them against CMB data helps evaluate their validity. Primordial gravitational waves could be another key. Generated during cosmic inflation, these waves might leave detectable signatures. Their detection would confirm aspects of early universe models. Advanced simulations help explore these possibilities. By modeling various scenarios, researchers can predict CMB patterns. Comparing these predictions with actual data tests the need for new physics. Future observations will further this investigation. Enhanced instruments will provide more detailed CMB measurements. These data will help confirm or refute the need for new theoretical frameworks. The quest for new physics is driven by anomalies that defy current understanding. Each unexplained feature in the CMB is a potential gateway to revolutionary discoveries. The search for these new principles continues to inspire cosmologists. The cosmic microwave background has profoundly influenced our understanding of the universe. It has provided a direct window into the early universe. This glimpse has helped refine models of cosmic evolution. The CMB confirmed the Big Bang theory as the leading explanation for the universe's origin. The uniformity and slight fluctuations in the CMB are consistent with a hot, dense beginning. This evidence solidified the Big Bang as the cornerstone of cosmology. By analyzing the CMB, scientists have determined the age of the universe. The precise measurement of 13.8 billion years helps frame the timeline of cosmic events. This age estimation is critical for understanding the universe's development. The CMB has revealed the composition of the universe. It showed that dark matter, dark energy, and normal matter make up the cosmos. This composition shapes our understanding of cosmic structure and dynamics. Fluctuations in the CMB have traced the formation of galaxies and clusters. They indicate how initial density variations grew into complex structures. This process is fundamental to the study of cosmic evolution. Polarization patterns in the CMB have provided insights into cosmic inflation. These patterns support the theory of rapid expansion just after the Big Bang. Inflation helps explain the large-scale structure of the universe. The CMB has influenced our understanding of the universe's geometry. Observations indicate that the universe is flat, which supports inflationary models. This geometric insight is crucial for cosmological theories. Gravitational lensing effects observed in the CMB have mapped the distribution of matter. These maps show how matter is spread throughout the universe. This distribution affects the formation and evolution of cosmic structures. The study of the CMB has refined the values of fundamental cosmological parameters. Parameters like the Hubble constant, dark matter density, and dark energy density have been measured with high precision. These values are essential for accurate cosmological models. The CMB has also provided evidence for the Revolutionizing epoch. This period saw the formation of the first stars and galaxies. Understanding Revolutionization helps explain how the universe evolved from its early state to its current form. Insights into neutrinos have been gained through CMB observations. The data suggests the existence of a specific number of light, weakly interacting particles. This information is vital for particle physics and cosmology. The integrated Sachs-Wolf effect observed in the CMB supports the existence of dark energy. This effect results from changes in gravitational potential impacting CMB photons. It provides another piece of evidence for the universe's accelerated expansion. CMB research has influenced the study of modified gravity theories. Observations test the predictions of these theories against the CMB data. This helps evaluate the need for changes to general relativity. The influence of the CMB extends to the search for new physics. Anomalies and unexplained features prompt the development of new theoretical models. These models aim to explain what current theories cannot. The continuous study of the CMB drives advancements in cosmology. Each new observation and analysis adds to our understanding. This ongoing research is essential for unraveling the universe's deepest mysteries. The cosmology community has responded to the discoveries of the CMB with great enthusiasm. Researchers worldwide have focused on analyzing the data. This collaborative effort has led to significant advancements in the field. Some scientists have expressed skepticism about certain anomalies. They argue that more data and improved methods are needed. This cautious approach ensures rigorous testing and validation of results. Others have embraced the anomalies as opportunities for new discoveries. These unexplained features drive the search for new physics. The potential for groundbreaking findings excites many in the community. The debate over the axis of evil has been particularly intense. Some researchers see it as a statistical fluke. Others believe it hints at fundamental new physics, prompting ongoing discussions and studies. The discovery of the cold spot has sparked diverse theories. Some suggest it could be a sign of a multiverse. Others propose more conventional explanations, such as a supervoid, highlighting the variety of perspectives. Responses to polarization patterns have been overwhelmingly positive. These patterns provide crucial tests for inflationary theory. The community has united in efforts to detect B modes, which would confirm inflation. The refined measurements of cosmological parameters have been widely accepted. These values are now fundamental to the standard model of cosmology. They guide current and future research in the field. The implications of gravitational lensing in the CMB have been well received. This phenomenon helps map the distribution of dark matter. It's seen as a powerful tool for understanding cosmic structure. The idea of modified gravity has both supporters and critics. Some researchers are intrigued by the potential for new theories. Others remain committed to general relativity, emphasizing the need for more evidence. The concept of a multiverse remains controversial. While it offers an explanation for certain anomalies, it's difficult to test. This idea continues to inspire debate and theoretical exploration. Responses to the idea of dark energy influencing the CMB are generally positive. The data aligns with the accelerated expansion of the universe. This consistency reinforces the dark energy hypothesis. The community has embraced the role of advanced simulations. These simulations help interpret CMB data and test theories. They are an essential part of modern cosmological research. Efforts to separate foreground contamination from the CMB are widely supported. Accurate measurements depend on this separation. Researchers continuously develop better methods to achieve this. The importance of cross-validation with different datasets is recognized. Consistent results across multiple observations strengthen findings. This practice is a cornerstone of reliable cosmological research. Future missions and technologies are eagerly anticipated. They promise to provide even more precise CMB measurements. The community looks forward to the new insights these advancements will bring. Overall, the cosmology community remains dynamic and engaged. The study of the CMB continues to inspire collaboration and innovation. This ongoing research is vital for deepening our understanding of the universe. The universe's topology refers to its overall shape and structure. Understanding the topology helps determine whether the universe is finite or infinite. It also affects how we perceive the cosmos on large scales. One possible topology is a flat, infinite universe. This model is consistent with current observations of the cosmic microwave background. It suggests the universe extends infinitely in all directions. Another possibility is a closed, finite universe. In this model, the universe curves back on itself, creating a finite volume. This could lead to a multi-connected space where traveling far enough in one direction brings you back to your starting point. An open universe is another option. This model describes a universe that curves outward, expanding forever. It implies an infinite expanse, but with a different geometry than the flat model. Topological features might leave imprints on the cosmic microwave background. Patterns in the CMB could reveal whether the universe has a complex topology. These imprints help cosmologists explore different models. The search for topological signatures involves studying the CMB's temperature fluctuations. Certain patterns might indicate a multi-connected universe. Identifying these patterns requires precise measurements and advanced analysis. Cosmic topology could explain some CMB anomalies. For instance, unusual alignments might result from the universe's shape. This idea offers an alternative perspective on observed anomalies. Observing repeated patterns in the CMB could suggest a finite topology. If the universe wraps around itself, the same structures might appear in different regions of the sky. Detecting such patterns would provide strong evidence for a multi-connected universe. Quantum gravity theories often predict specific topological features. These theories aim to unify general relativity with quantum mechanics. Observing the predicted features would support these advanced models. Large-scale structure surveys also contribute to understanding topology. By mapping galaxies and clusters, scientists can infer the universe's shape. These surveys complement CMB studies, providing a broader picture. Gravitational waves might offer insights into cosmic topology. These waves could carry information about the universe's overall structure. Detecting and analyzing them adds another layer to topological research. Future missions will enhance our ability to study topology. Improved CMB observations and galaxy surveys will provide more data. This progress will help refine models and test new theories. The role of dark matter and dark energy in shaping topology is also explored. Their influence on cosmic expansion and structure affects the overall shape. Understanding this relationship is key to a complete picture. The interplay between cosmic topology and fundamental physics is a rich field of study. It bridges cosmology, particle physics, and general relativity. This interdisciplinary approach drives innovative research. The quest to understand the universe's topology continues to inspire cosmologists. Each new discovery brings us closer to understanding the cosmos. The study of topology remains a vital part of unraveling the universe's mysteries. Local foregrounds are sources of radiation that interfere with the cosmic microwave background. They include emissions from our galaxy, such as dust, gas, and synchrotron radiation. These foregrounds can distort the CMB signal and must be carefully removed. Galactic dust is a significant source of contamination. Dust grains in the Milky Way emit radiation that can mask the faint CMB signal. This emission varies across the sky, complicating CMB measurements. Synchrotron radiation is another major foreground. It results from high-energy electrons spiraling in magnetic fields. This radiation affects lower-frequency observations and needs to be accounted for. Free emission, or Bremsstrahlung, also contributes to foreground noise. It occurs when electrons interact with ions, emitting radiation. This process is more prominent at higher frequencies. To separate the CMB from these local foregrounds, scientists use multi-frequency observations. By observing the sky at different wavelengths, they can identify and subtract foreground emissions. This method improves the accuracy of CMB maps. Data processing techniques, such as component separation algorithms, are essential. These algorithms analyze the data to isolate the CMB signal. They help distinguish between the cosmic background and local sources. Polarization measurements are particularly affected by foregrounds. Galactic dust can polarize light, mimicking CMB polarization patterns. Advanced techniques are required to filter out these contributions. Foreground contamination can vary significantly across the sky. Some regions are more affected by dust and other emissions. Scientists carefully select observation fields to minimize these effects. The Planck satellite made significant advancements in foreground removal. Its multi-frequency instruments provided detailed maps of foreground emissions. These maps are crucial for accurate CMB studies. Ground-based telescopes also contribute to understanding foregrounds. Observatories like the Atacama Cosmology Telescope conduct high-resolution surveys. Their data helps refine models of galactic emissions. Future missions will continue to improve foreground separation. Enhanced sensitivity and resolution will lead to better data. This progress is vital for isolating the true CMB signal. Collaboration between different observational platforms enhances this effort. Combining data from satellites, balloons, and ground-based telescopes provides a comprehensive view. This approach ensures more reliable foreground removal. Foreground studies also offer insights into our galaxy. Understanding these emissions helps map the structure and composition of the Milky Way. This knowledge is valuable for both cosmology and galactic astronomy. The challenge of local foregrounds highlights the complexity of CMB research. Accurate measurements depend on effectively managing these contaminations. This ongoing effort is essential for advancing our understanding of the universe. By addressing local foregrounds, scientists can obtain a clearer view of the CMB. This clarity is crucial for exploring fundamental questions about the cosmos. The study of foregrounds remains a critical component of cosmological research. Exotic physics models propose new ideas beyond the standard cosmological theories. These models aim to explain anomalies in the cosmic microwave background and other cosmic phenomena. They often incorporate concepts from quantum mechanics and high-energy physics. One such model involves the idea of extra dimensions. Theories like string theory suggest additional spatial dimensions beyond the familiar three. These extra dimensions could influence cosmic evolution and leave imprints on the CMB. Another exotic model is the concept of brane cosmology. In this framework, our universe is a three-dimensional brane within a higher dimensional space. Interactions between branes might create observable effects in the CMB. The idea of varying physical constants over time is also explored. Some models suggest that constants like the speed of light or gravitational constant could change. These variations could impact cosmic evolution and CMB measurements. Primordial black holes are another exotic concept. These black holes, formed in the early universe, could affect the distribution of matter and radiation. Detecting their influence on the CMB would provide new insights into the early cosmos. Dark matter candidates beyond the standard model are considered. Exotic particles like axions or sterile neutrinos might compose dark matter. Their interactions could leave unique signatures in the CMB. The theory of loop quantum gravity offers an alternative to string theory. It attempts to quantize space-time itself, potentially resolving singularities. Predictions from this theory could be tested against CMB observations. Modified gravity theories propose changes to general relativity. Models like MOND or TVES suggest different behaviors at cosmic scales. These modifications aim to explain phenomena like dark matter and cosmic acceleration. The concept of holography is also explored. It suggests that all the information in our universe might be encoded on a two-dimensional surface. This idea has profound implications for understanding black holes and the Big Bang. Some exotic models propose interactions between dark matter and dark energy. These interactions could influence the universe's expansion and structure. Detecting their effects in the CMB would validate these theories. The idea of cosmic strings or other topological defects is revisited. These hypothetical structures from the early universe could leave detectable imprints. Observing such imprints would support these advanced models. Quantum entanglement on a cosmic scale is another intriguing concept. It suggests that particles across vast distances could be entangled, affecting the CMB. This idea bridges quantum mechanics and cosmology. Theories involving a cyclic universe propose an endless series of expansions and contractions. Each cycle could leave residual effects on the CMB. Detecting these effects would challenge the conventional Big Bang model. The possibility of an antimatter-dominated region in the universe is considered. If large regions were dominated by antimatter, it would affect cosmic evolution. Observing these effects in the CMB would have significant implications. Some models explore the idea of a multiverse. Different universes with varying physical laws might interact, influencing the CMB. This speculative idea opens new avenues for theoretical research. Exotic physics models push the boundaries of our understanding. They challenge existing theories and propose new mechanisms for cosmic phenomena. Testing these models against observations is essential for advancing cosmology. The statistical fluke hypothesis suggests that some anomalies in the cosmic microwave background might occur by chance. Given the vast amount of data, random fluctuations could create patterns that appear significant. This hypothesis challenges the interpretation of certain observed anomalies. Researchers use statistical methods to evaluate this possibility. They compare the observed data to simulations of random CMB maps. If the anomalies are common in these simulations, they might be statistical flukes. The axis of evil is a prime candidate for this hypothesis. Some studies suggest that the alignment could be a rare but possible outcome of random fluctuations. This interpretation questions the need for new physics to explain the alignment. The cold spot is also examined under this hypothesis. Its unusual characteristics could be the result of a random chance. Statistical analysis helps determine the likelihood of such a feature occurring naturally. The hemispherical power asymmetry might be another example. While it challenges isotropy, it could also be a product of statistical variation. Evaluating its significance requires careful statistical testing. To test the statistical fluke hypothesis, scientists generate numerous simulated CMB maps. These simulations are based on the standard cosmological model. By comparing them to actual observations, researchers assess the probability of anomalies. P-values are used to quantify the likelihood of anomalies being random. A low p-value indicates that the anomaly is unlikely to be a fluke. High p-values suggest that it might occur naturally in a random distribution. Cross-validation with different datasets strengthens the analysis. Consistent anomalies across various observations reduce the likelihood of a statistical fluke. This approach helps confirm or refute the hypothesis. Foreground contamination must be accounted for in these studies. Local sources of radiation can mimic or amplify anomalies. Removing these effects ensures that the analysis focuses on genuine cosmic features. Instrumental errors are another consideration. Calibration issues or data processing artifacts could create false patterns. Ensuring high data quality is essential for reliable statistical testing. Even if some anomalies are statistical flukes, others might still require new explanations. The presence of a few flukes does not negate the potential for groundbreaking discoveries. It highlights the importance of distinguishing between chance and significant patterns. Ongoing research aims to refine these statistical methods. Improved techniques provide more accurate assessments of anomaly significance. This continuous improvement is vital for advancing cosmological studies. Future observations will provide additional data to test this hypothesis. Enhanced sensitivity and resolution will reveal more details. These observations will help determine whether certain anomalies are indeed flukes. The statistical fluke hypothesis encourages a cautious approach to interpreting data. It reminds scientists to consider all possibilities before concluding. This rigorous approach is crucial for building a robust understanding of the universe. Ultimately, the goal is to separate random fluctuations from meaningful signals. This distinction helps identify truly significant features in the CMB. Understanding these features is essential for unraveling the mysteries of the cosmos. Multiverse theory proposes that our universe is just one of many. These multiple universes may have different physical laws and constants. This idea expands the scope of cosmology beyond our observable universe. Some multiverse models suggest that each universe is a separate bubble in a vast cosmic foam. These bubbles can form, collide, and separate. Our universe could be one such bubble in this larger multiverse. Another version of the theory is based on the concept of cosmic inflation. During inflation, different regions of space could have expanded at different rates, creating separate universes. Each universe might have its own distinct properties. String theory also supports the multiverse idea. It suggests that there could be many possible configurations of space-time. Each configuration could correspond to a different universe with its own set of physical laws. The multiverse theory could explain certain anomalies in the cosmic microwave background. For example, interactions with other universes might leave imprints on the CMB. These imprints could manifest as unexpected patterns or alignments. The cold spot might be a sign of such an interaction. Some theories suggest it could result from a collision with another universe. This idea, while speculative, provides a possible explanation for the anomaly. The concept of a multiverse raises profound philosophical and scientific questions. It challenges our understanding of reality and the nature of existence. If true, it implies that our universe is just one of countless others. Testing the multiverse theory is challenging. By definition, other universes are beyond our observable horizon. However, indirect evidence, such as anomalies in the CMB, might offer clues. Some scientists argue that the multiverse theory is untestable and therefore not scientific. Others believe it opens new avenues for understanding the cosmos. The debate over its validity continues in the scientific community. Observational evidence might come from advanced cosmic surveys. These surveys could reveal subtle signs of other universes. Researchers are exploring various methods to detect such evidence. The multiverse theory also intersects with quantum mechanics. It suggests that all possible outcomes of quantum events actually occur in separate universes. This idea aligns with the many worlds interpretation of quantum mechanics. If the multiverse theory is correct, it could solve some long-standing puzzles in physics. It might explain why our universe has the specific properties that allow life to exist. Each universe in the multiverse could have different properties, and we happen to live in one that supports life. Critics argue that the theory lacks empirical support. They caution against relying on speculative ideas without concrete evidence. The scientific method demands rigorous testing and validation. Proponents of the multiverse theory emphasize its explanatory power. It offers potential solutions to complex cosmological problems. Continued research and exploration are needed to evaluate its merits. The multiverse theory represents a bold and imaginative step in cosmology. It challenges us to think beyond our observable universe. Whether it is ultimately proven or not, it inspires ongoing inquiry and debate. Main criticisms of the axis of evil focus on its statistical significance. Some scientists argue that the alignment could be a coincidence. They suggest it might not be as meaningful as it appears. Another criticism involves the data quality. Early observations, like those from the WMAP satellite, had limitations. Some researchers believe these limitations could have introduced biases. Foreground contamination is a major concern. Galactic emissions and other local sources might distort the CMB signal. Critics argue that these contaminations need more thorough analysis. Instrumental effects are also scrutinized. Calibration errors or systematic biases could create false patterns. Ensuring high precision in measurements is crucial to address this issue. The choice of coordinate system impacts the analysis. Some alignments might appear significant in one system but not in another. This dependency raises questions about the robustness of the findings. Cosmological models predict isotropy on large scales. The axis of evil challenges this prediction, but some believe the models are still valid. They argue that more data and refined models are needed for a definitive conclusion. Critics also point to the lack of independent confirmation. The alignment should be verified with different datasets and methods. Consistency across multiple observations would strengthen its validity. Some researchers emphasize the need for more advanced simulations. Simulations help determine whether the alignment could occur by chance. Improved models provide better context for interpreting the data. There is also debate over the definition of anomalies. What qualifies as an anomaly can be subjective. Clear, objective criteria are necessary for meaningful analysis. Another criticism is the focus on a single feature. The CMB contains many patterns and structures. focusing solely on the axis of evil might overlook other important aspects. Theoretical implications of the alignment are still unclear. While it challenges isotropy, it doesn't necessarily point to specific new physics. More theoretical work is needed to understand its significance. Critics argue that anomalies like the axis of evil might distract from other research. They caution against overemphasizing one feature at the expense of broader studies. A balanced approach is essential for comprehensive understanding. Some suggest that future missions will clarify the issue. More precise data from upcoming satellites could confirm or refute the alignment. Continued observation is crucial for resolving these debates. The scientific community values rigorous testing and skepticism. Criticisms of the axis of evil reflect this commitment to thorough investigation. Healthy debate drives progress and ensures robust conclusions. Ultimately, the criticisms highlight the complexity of cosmological research. Understanding the universe requires careful analysis and consideration of multiple factors. The study of the axis of evil continues to evolve with ongoing research. Arguments against the significance of the axis of evil often begin with statistical concerns. Some scientists believe the alignment is a result of data dredging. This process can lead to finding patterns that aren't genuinely significant. Critics also highlight the issue of cosmic variance. Cosmic variance refers to the statistical uncertainty inherent in observing only one universe. This uncertainty can make it difficult to draw firm conclusions about anomalies. Another argument is the potential for selection bias. Researchers might unintentionally emphasize data that supports the alignment. This bias can skew interpretations and overstate the significance of findings. Instrumental and observational limitations are frequently cited. Early data, particularly from WMAP, had imperfections. These imperfections could introduce artifacts that mimic significant patterns. The impact of foreground contamination cannot be overstated. Emissions from the Milky Way and other sources might distort the CMB. Critics argue that these factors need more rigorous separation. Some argue that the alignment is sensitive to the chosen coordinate system. When analyzed in different systems, the alignment may not appear as striking. This sensitivity undermines claims of its significance. The lack of independent verification is another point of contention. True scientific significance requires confirmation across multiple data sets. So far, consistent confirmation remains elusive. Some researchers suggest that the alignment could be a coincidence. Given the vast amount of data, occasional unusual patterns are expected. These patterns might not indicate any deeper physical reality. The focus on the axis of evil might be disproportionate. The CMB contains many complex features. Overemphasis on one anomaly can detract from a broader understanding. There is also skepticism about the theoretical implications. While intriguing, the alignment doesn't necessarily point to new physics. It might not warrant the dramatic interpretations some suggest. Critics highlight that cosmological models still largely predict isotropy. The standard model remains robust despite the anomaly. They argue that the axis of evil doesn't fundamentally challenge this model. Concerns about the reproducibility of results are also raised. If the alignment cannot be consistently reproduced, its significance is questionable. Reliable scientific conclusions depend on reproducibility. Some argue that future data might resolve the issue. Improved observations could clarify whether the alignment is real or illusory. Patience and continued research are necessary for a definitive answer. The debate illustrates the self-correcting nature of science. Skepticism and rigorous testing are essential for progress. These arguments ensure that conclusions about the axis of evil are robust. Ultimately, the arguments against its significance reflect the complexities of cosmology. Understanding such anomalies requires careful, unbiased analysis. Ongoing research and debate will continue to shed light on these intriguing observations. Alternative interpretations of the axis of evil seek to explain the anomaly without invoking new physics. One interpretation is that the alignment is a statistical artifact. This view suggests the pattern might be a rare but natural occurrence in random data. Another interpretation involves local foregrounds. Galactic emissions and cosmic dust could distort the CMB signal. This contamination might create the illusion of an alignment. Some researchers propose that instrumental effects are to blame. Calibration errors or systematic biases in the data collection process could produce false patterns. Ensuring precision in measurements is crucial to address this possibility. Cosmic variance is another consideration. This inherent uncertainty in observing a single universe might lead to misinterpretation of data. It suggests that some anomalies are expected due to random chance. The possibility of an unrecognized foreground source is also explored. Unknown or poorly understood astrophysical processes could affect the CMB. Identifying and accounting for these sources might resolve the anomaly. Large-scale structure influences are considered as well. The distribution of galaxies and clusters might impact the CMB in unexpected ways. This interaction could explain some of the observed alignments. Some theories suggest that the anomaly results from early universe conditions. Variations in initial conditions might leave imprints that we now observe as alignments. This view aligns with certain inflationary models. Alternative cosmological models propose different universe topologies. A universe with a non-trivial shape, such as a torus or a higher dimensional manifold, could produce unusual patterns. These topologies might naturally lead to observed alignments. The impact of dark energy and dark matter distributions is another area of exploration. Variations in these components could influence the CMB's appearance. This idea integrates well with existing cosmological models. Quantum effects in the early universe might also play a role. Fluctuations at quantum scales could leave large-scale imprints. Understanding these effects requires advanced theoretical frameworks. Modified gravity theories offer another explanation. Changes to our understanding of gravity on large scales could affect the CMB. Testing these theories against observational data is crucial for their validation. Interactions with other universes in a multiverse scenario could also be a factor. Collisions or influences from neighboring universes might leave detectable marks. This speculative idea opens new avenues for theoretical exploration. Cosmic strings or other topological defects might explain the anomaly. These hypothetical structures from the early universe could create distinctive imprints. Observing such imprints would support these advanced models. Advanced simulations help test these alternative interpretations. By recreating various scenarios, researchers can predict how the CMB should appear. Comparing these predictions with actual data provides insights into the validity of different theories. Ongoing observations and future missions will provide more data. Enhanced sensitivity and resolution will reveal new details. These advancements will help clarify the nature of the axis of evil and its underlying causes. Proponents of the axis of evil argue that the alignment is too significant to be a coincidence. They believe it warrants serious consideration and further investigation. This perspective drives ongoing research and theoretical exploration. Some proponents suggest that the alignment indicates new physics. They see it as a potential breakthrough in our understanding of the universe. This view motivates the search for underlying causes beyond current models. Others emphasize the need for more data to confirm the anomaly. They advocate for additional observations with improved instruments. This approach aims to gather robust evidence to support their claims. Proponents often highlight the consistency of the alignment across different datasets. They point out that the axis of evil appears in both WMAP and Planck data. This consistency strengthens their argument for its significance. They also argue that the alignment challenges the standard cosmological model. This challenge, they believe, could lead to new insights and discoveries. They see the axis of evil as an opportunity to advance cosmology. Some researchers propose that the anomaly could reveal hidden properties of the universe. They suggest that the alignment might hint at unknown aspects of cosmic structure. This perspective encourages the development of new theoretical models. Proponents emphasize the need for interdisciplinary approaches. They believe that combining insights from cosmology, quantum mechanics, and general relativity could uncover the truth. This holistic approach is seen as essential for progress. They often call for more sophisticated simulations. Advanced modeling techniques could help explain the alignment. These simulations are crucial for testing various hypotheses and interpretations. Proponents also focus on the importance of precision in measurements. They argue that refining data collection methods could eliminate doubts about the alignment. High-quality data is seen as key to resolving the debate. Some highlight the potential for the alignment to inspire new research areas. They see it as a catalyst for innovative ideas and experiments. This inspiration drives a broader scientific inquiry. Proponents often point to the historical context of scientific breakthroughs. They remind skeptics that many significant discoveries were initially controversial. This perspective frames the axis of evil as a possible precursor to major advancements. They stress the value of keeping an open mind. Exploring unconventional ideas might lead to unexpected findings. This open-mindedness is viewed as essential for scientific progress. Proponents argue that the axis of evil could unify different cosmological theories. If understood, it might bridge gaps between competing models. This unifying potential is seen as a powerful motivation for further study. They frequently call for increased collaboration in the scientific community. Sharing data and ideas across disciplines could accelerate understanding. This collaborative spirit is seen as vital for addressing complex anomalies. Ultimately, proponents of the axis of evil advocate for thorough investigation. They believe that dismissing the alignment without proper study is premature. This commitment to rigorous inquiry reflects their dedication to advancing cosmology. Peer review and reproducibility are fundamental in validating scientific findings. They ensure that results are reliable and not the product of errors or biases. In the case of the axis of evil, these processes are especially crucial. The initial findings of the axis of evil underwent rigorous peer review. Scientists scrutinized the methods, data, and interpretations. This review process aimed to confirm the validity of the results. Reproducibility is a key aspect of scientific integrity. Independent teams must be able to replicate the findings using different data and methods. For the axis of evil, reproducibility would strengthen the case for its significance. Multiple data sets have been used to test the axis of evil. Observations from WMAP and Planck are compared. Consistent results across these data sets add credibility to the anomaly. Independent analyses are vital for confirmation. Different research groups have conducted their own studies on the axis of evil. These studies help verify the original findings and explore alternative explanations. The role of simulations in reproducibility is significant. Simulations help predict what the CMB should look like under various conditions. Comparing these predictions with actual observations tests the anomaly's robustness. Peer review also involves assessing the statistical methods used. Accurate statistical analysis is essential for determining the likelihood of the anomaly. Peer reviewers examine these methods to ensure they are sound. Critics of the axis of evil often focus on reproducibility. They argue that if the anomaly cannot be consistently replicated, its significance is doubtful. This perspective emphasizes the need for multiple confirmations. Reproducibility issues can arise from data quality. Ensuring high precision in measurements and calibration is critical. Any discrepancies in data collection can affect the results. Transparency in research is crucial for reproducibility. Sharing data and methods openly allows other scientists to replicate the study. This openness is a cornerstone of the scientific process. Peer review also considers the potential for systematic errors. Reviewers look for biases that might have influenced the findings. Identifying and correcting these biases is essential for reliable results. The community's response to peer-reviewed findings shapes future research. Positive reviews and successful replications lead to broader acceptance. Conversely, negative reviews and failed replications prompt re-evaluation. The process of peer review and reproducibility drives scientific progress. It ensures that only robust, well-supported findings become part of the scientific consensus. This process is essential for advancing our understanding of the universe. For the axis of evil, ongoing peer review and reproducibility efforts are necessary. As new data becomes available, these processes will continue to test the anomaly. The commitment to rigorous evaluation reflects the scientific method's core principles. Ultimately, peer review and reproducibility aim to establish the truth. They separate genuine discoveries from artifacts and errors. This pursuit of truth is fundamental to the advancement of cosmology. Instrumentation and calibration issues are critical when studying the cosmic microwave background. Precise instruments are needed to detect the faint signals from the early universe. Any errors can significantly impact the results. Satellites like WMAP and Planck have been designed to minimize these issues. They use highly sensitive detectors to measure temperature fluctuations in the CMB. However, even these advanced instruments are not immune to problems. Calibration is a major challenge. Instruments must be carefully calibrated to ensure accurate measurements. This involves comparing the instrument's readings with known standards. Any miscalibration can introduce biases into the data. Thermal fluctuations in the instruments themselves can affect the measurements. Satellites in space face extreme temperature variations. These fluctuations need to be accounted for to ensure data accuracy. Electronic noise is another concern. The detectors in these satellites can pick up unwanted electronic signals. This noise must be filtered out to isolate the true cosmic signal. Foreground contamination also complicates instrumentation. Emissions from our galaxy and other sources can interfere with CMB measurements. Instruments must be designed to distinguish between these foregrounds and the CMB. The position and orientation of the satellite can impact data quality. Precise control over these factors is necessary to avoid distortions. Small errors in positioning can lead to significant data inaccuracies. Instrument aging is another factor. Over time, the sensitivity of detectors can degrade. Continuous calibration and maintenance are needed to keep the instruments functioning correctly. Cross-calibration with other instruments is essential. Comparing data from different satellites helps identify and correct discrepancies. This process ensures more reliable and consistent results. Software algorithms play a crucial role in data processing. They are used to filter noise, correct for calibration errors, and separate foregrounds. Ensuring these algorithms are accurate and reliable is vital. Instrumental artifacts can sometimes mimic cosmic features. Patterns introduced by the instruments themselves can be mistaken for real anomalies. Identifying and correcting these artifacts is necessary for accurate interpretation. Laboratory tests on the ground help prepare for space missions. These tests simulate the conditions the instruments will face. They are crucial for identifying potential issues before launch. Continuous monitoring of instruments in space is required. Any deviations in their performance need to be promptly addressed. This ongoing oversight helps maintain data quality. Redundancy in instrumentation is a common practice. Using multiple detectors and systems provides backup and cross-checking. This redundancy enhances the reliability of the data. Addressing instrumentation and calibration issues is fundamental for CMB research. Ensuring high precision and accuracy in measurements underpins the validity of scientific findings. This meticulous attention to detail drives the success of cosmological studies. Data analysis techniques are crucial for interpreting the cosmic microwave background. These techniques help extract meaningful information from the raw data collected by satellites. Advanced methods are employed to ensure the accuracy and reliability of the results. One key technique is map making. This involves converting the raw data into temperature maps of the sky. These maps show the tiny fluctuations in the CMB that provide insights into the early universe. Fourier analysis is used to study these fluctuations. By breaking down the temperature variations into different frequency components, scientists can analyze the underlying patterns. This analysis is essential for understanding the power spectrum of the CMB. The power spectrum reveals the distribution of temperature fluctuations at different scales. Peaks in the power spectrum correspond to specific physical processes in the early universe. Analyzing these peaks helps refine cosmological models. Component separation is another critical technique. The data collected by satellites includes emissions from the Milky Way and other foreground sources. Advanced algorithms are used to separate these components from the true CMB signal. Statistical methods play a vital role in data analysis. Techniques like Bayesian inference help quantify the uncertainties in the measurements. This statistical rigor ensures that the conclusions drawn from the data are robust. Machine learning algorithms are increasingly used in CMB research. These algorithms can identify patterns and anomalies in the data that might be missed by traditional methods. They enhance the efficiency and accuracy of data analysis. Cross-correlation is employed to compare data from different sources. By analyzing how the data from various observations relate to each other, scientists can validate their findings. This cross-checking is essential for confirming the consistency of the results. Monte Carlo simulations are used to model the CMB data. These simulations generate synthetic datasets based on theoretical models. Comparing these simulations with actual observations helps test the validity of different cosmological theories. Wavelet analysis is another technique used to study the CMB. It allows scientists to analyze the data at multiple scales simultaneously. This multi-scale analysis provides a more detailed understanding of the temperature fluctuations. Anisotropy analysis focuses on studying the variations in the CMB across different directions. This analysis helps identify any deviations from the expected uniformity of the universe. It is crucial for understanding anomalies like the axis of evil. Gravitational lensing analysis examines the distortions in the CMB caused by massive objects. These distortions provide information about the distribution of matter in the universe. Analyzing them helps refine models of cosmic structure. Polarization analysis studies the patterns of polarized light in the CMB. These patterns carry additional information about the early universe. Techniques for analyzing polarization data are essential for testing theories of cosmic inflation. Foreground modeling involves creating detailed models of the emissions from local sources. These models are used to subtract the foreground contamination from the CMB data. Accurate modeling is critical for isolating the true cosmic signal. Noise reduction techniques are applied to enhance data quality. By filtering out random electronic noise, scientists can improve the clarity of the CMB maps. These techniques ensure that the final results are as accurate as possible. Data analysis techniques are continuously evolving. Advances in computational power and algorithm development drive this progress. These innovations are essential for deepening our understanding of the universe through CMB research. Satellite missions have been instrumental in advancing our understanding of the cosmic microwave background. Missions like WMAP and Planck have provided detailed maps of the CMB. These maps have revolutionized cosmology by offering insights into the early universe. WMAP, launched in 2001, was designed to measure temperature fluctuations in the CMB. It provided high-resolution data that confirmed key predictions of the Big Bang theory. WMAP's observations helped refine the values of fundamental cosmological parameters. Planck, launched in 2009, took these measurements to an even higher level of precision. Planck's instruments covered a wider range of frequencies, allowing for more detailed analysis. The mission's data has been crucial for understanding the fine structure of the CMB. Both satellites have contributed to measuring the universe's age. By analyzing the CMB, WMAP and Planck estimated the universe to be about 13.8 billion years old. This precise age helps frame the timeline of cosmic evolution. These missions have also provided evidence for dark energy and dark matter. Observations from WMAP and Planck showed that dark energy makes up about 70% of the universe. Dark matter accounts for about 25%, while normal matter makes up the rest. The detailed maps produced by these satellites have confirmed the universe's flat geometry. Planck's data, in particular, has shown that the universe is remarkably flat. This supports the inflationary model of the early universe. Polarization measurements from these missions have tested theories of cosmic inflation. Planck's observations of E-mode polarization patterns align with inflationary predictions. Detecting B-mode polarization would provide further confirmation. Satellite missions have also mapped the distribution of matter through gravitational lensing. This technique measures how massive objects distort the CMB. These maps help understand the large-scale structure of the universe. Foreground separation has been a key achievement of these missions. WMAP and Planck have developed advanced methods to remove emissions from the Milky Way. This process isolates the true cosmic signal for more accurate analysis. The data from these satellites have helped measure the Hubble constant. This constant describes the rate of the universe's expansion. Precise measurements from WMAP and Planck contribute to ongoing debates about its exact value. These missions have provided insights into the Revolutionizing epoch. By studying the CMB, scientists can understand how the first stars and galaxies formed. This period is crucial for understanding the universe's transition from darkness to light. Planck's data has offered evidence for neutrino properties. Observations suggest the existence of a specific number of light, weakly interacting particles. This information is important for both cosmology and particle physics. The success of WMAP and Planck has inspired future missions. New satellites will build on their legacy, providing even more precise data. These missions will continue to refine our understanding of the cosmos. The role of satellite missions in cosmology cannot be overstated. They have provided a wealth of data that drives scientific discovery. Their contributions are essential for advancing our knowledge of the universe. Ongoing and future missions promise to reveal even more about the CMB. Enhanced technology and better resolution will uncover new details. The study of the CMB through satellite missions remains a cornerstone of modern cosmology. Advances in observational technology have dramatically enhanced our ability to study the universe. These technological improvements provide clearer, more detailed images of the cosmic microwave background. This progress has led to significant breakthroughs in cosmology. High-resolution detectors are a key advancement. Modern detectors can measure minute temperature fluctuations in the CMB with incredible precision. This precision allows scientists to analyze the fine details of the early universe. Multi-frequency observations are another important development. Observing the CMB at different frequencies helps separate cosmic signals from local foregrounds. This separation is crucial for obtaining accurate data. Space-based telescopes have revolutionized our observational capabilities. Instruments like those on the Planck satellite operate above Earth's atmosphere. This positioning eliminates atmospheric interference, leading to clearer observations. Cryogenic technology is essential for cooling detectors. By operating at extremely low temperatures, these detectors can reduce electronic noise. Lower noise levels improve the sensitivity of the measurements. Interferometry has advanced the study of cosmic structures. This technique combines signals from multiple telescopes to create a detailed image. It enhances resolution and helps map large-scale cosmic features. Data processing algorithms have seen significant improvements. These algorithms filter out noise, correct for instrumental biases, and separate foregrounds. Enhanced processing techniques lead to more accurate and reliable data. The use of supercomputers has transformed data analysis. Complex simulations and detailed modeling of the CMB are now possible. Supercomputers allow researchers to process vast amounts of data quickly and accurately. Ground-based observatories have also benefited from technological advances. Telescopes like the South Pole Telescope use advanced detectors and cooling systems. These upgrades increase their sensitivity and accuracy. Balloon-borne experiments provide another platform for CMB observations. High-altitude balloons carry instruments above much of the atmosphere. This method offers a cost-effective way to gather high-quality data. Spectroscopic techniques have improved our understanding of cosmic composition. These techniques analyze the spectrum of light from cosmic sources. They provide detailed information about the elements and molecules present. Adaptive optics technology corrects for atmospheric distortions. By adjusting mirrors in real time, telescopes can produce sharper images. This technology is particularly useful for ground-based observations. Advances in polarization measurement techniques have been significant. Improved detectors can now measure the faint polarization patterns in the CMB. These measurements provide additional insights into the early universe. Automated observation systems enhance data collection efficiency. These systems allow for continuous monitoring and quick adjustments. Automation ensures that no important data is missed. Collaboration between international space agencies has accelerated technological progress. Joint missions and shared resources lead to more comprehensive studies. This collaboration drives the development of cutting-edge observational tools. The continuous evolution of observational technology promises to unlock new cosmic secrets. Each technological leap provides deeper insights into the universe. These advancements are fundamental to the ongoing exploration of the cosmos. Future missions and experiments promise to expand our understanding of the cosmic microwave background. These projects aim to provide even more detailed data than previous missions. They will continue to refine our knowledge of the early universe. The upcoming LightBird mission is designed to measure the polarization of the CMB with high precision. LightBird will help detect B-mode polarization, providing insights into cosmic inflation. This mission is expected to launch in the 2020s. The Simons Observatory, a ground-based project, will significantly enhance CMB observations. Equipped with advanced detectors, it will measure temperature and polarization fluctuations. The observatory aims to improve constraints on cosmological parameters. The CMB-S4 project represents the next generation of ground-based CMB experiments. It will deploy a series of telescopes at multiple sites to cover a wide range of frequencies. This project will offer unprecedented sensitivity and resolution. NASA's proposed PICO satellite aims to map the CMB with extraordinary detail. PICO will measure temperature and polarization across the entire sky. Its data will help test theories of the early universe and dark matter. The James Webb Space Telescope, though not specifically a CMB mission, will complement CMB studies. Its infrared observations will provide insights into the revolutionizing epoch and early galaxy formation. This context is crucial for interpreting CMB data. Ground-based arrays like the Atacama Cosmology Telescope will continue to play a vital role. These telescopes will enhance our understanding of the CMB through high-resolution imaging. Their data will be essential for cross-checking satellite observations. Balloon-borne experiments like SPIDER will offer unique perspectives. Operating above much of the atmosphere, SPIDER will measure CMB polarization with high sensitivity. These experiments provide valuable complementary data to satellite missions. Future missions will also focus on improving foreground separation techniques. Advanced instruments will better distinguish between cosmic signals and local emissions. This separation is crucial for isolating the true CMB signal. International collaboration will be key to the success of these missions. Shared resources and expertise will lead to more comprehensive and detailed studies. Global partnerships will enhance the scientific return from these projects. Theoretical advancements will guide observational strategies. Improved models of cosmic inflation and dark matter will shape mission goals. These theories will help interpret the data collected by future experiments. Technological innovations will continue to drive progress. New detector materials, cooling techniques, and data processing algorithms will enhance capabilities. These innovations will enable more precise and accurate measurements. Education and outreach will be integral to future missions. Engaging the public and inspiring the next generation of scientists is essential. Clear communication of scientific goals and discoveries will foster broader support for cosmological research. The interplay between observations and simulations will deepen our understanding. Future missions will rely on advanced simulations to interpret their findings. These simulations will help test and refine cosmological theories. Ongoing missions will build on the legacy of WMAP and Planck. Each new project will provide a more detailed picture of the CMB. This cumulative knowledge will drive the next wave of discoveries in cosmology. The future of CMB research is bright and full of potential. With upcoming missions and experiments, we are poised to uncover new secrets of the universe. These efforts will continue to advance our understanding of the cosmos. The cold spot is one of the most intriguing anomalies in the cosmic microwave background. It appears as a large, unusually cold region in the CMB data. This anomaly was first detected by the WMAP satellite. The cold spot is located in the southern hemisphere of the sky. Its temperature is significantly lower than the surrounding areas. This temperature deviation is difficult to explain with standard cosmological models. Various hypotheses have been proposed to explain the cold spot. One idea is that it is a statistical fluke. Given the vast amount of data, some regions might naturally exhibit unusual temperatures. Another hypothesis suggests the presence of a supervoid. A supervoid is a large region with fewer galaxies and less matter. This lack of matter could cause the observed temperature drop. Some researchers propose that the cold spot could be evidence of a collision with another universe. This idea is speculative but intriguing. It suggests that our universe might interact with other universes in a multiverse. Foreground contamination is also considered a potential cause. Galactic dust or other emissions might distort the CMB signal. Careful analysis is needed to rule out these local effects. Instrumental errors are another possible explanation. Calibration issues or data processing artifacts could create false patterns. Ensuring high data quality is crucial to address this possibility. The cold spot has been studied using data from both WMAP and Planck. Both satellites confirmed the existence of this anomaly. Their observations provide a robust data set for further analysis. Some studies have explored the impact of the cold spot on the isotropy of the universe. Isotropy means the universe looks the same in all directions. The existence of the cold spot challenges this assumption. Researchers have also examined the cold spot's influence on large-scale structure formation. A supervoid or similar feature could affect the distribution of galaxies and clusters. Understanding this impact helps refine cosmological models. Advanced simulations are used to test different hypotheses. These simulations recreate the conditions that might produce a cold spot. Comparing these models with actual data helps identify the most plausible explanations. Ongoing observations continue to provide new insights. Future missions with improved sensitivity will offer more detailed data. These observations are crucial for understanding the true nature of the cold spot. The cold spot remains a topic of active research and debate. It challenges our current understanding of the universe. Resolving its origin could lead to significant breakthroughs in cosmology. Public interest in the cold spot highlights the importance of communicating scientific discoveries. Engaging the public with intriguing anomalies fosters a broader appreciation for cosmology. It also inspires the next generation of scientists. The cold spot exemplifies the mysteries that drive scientific inquiry. Each new discovery adds to our knowledge and raises new questions. The study of the cold spot continues to push the boundaries of our understanding of the cosmos. The dipole anomaly in the cosmic microwave background refers to a significant temperature difference across the sky. This difference creates a dipole pattern, with one side slightly warmer and the other slightly cooler. The dipole anomaly is well known and has been carefully studied. This dipole pattern is primarily attributed to the motion of our solar system relative to the rest of the universe. As the solar system moves through space, it causes a Doppler shift in the CMB radiation. This shift leads to the observed temperature difference. The magnitude of the dipole anomaly is relatively large compared to other fluctuations in the CMB. It is the most prominent feature in the CMB after the average temperature. This prominence makes it a key focus of CMB studies. Removing the dipole component is crucial for studying other, smaller fluctuations in the CMB. Scientists must account for this motion to accurately analyze the remaining anisotropies. This step is essential for understanding the early universe. There are still some debates about the exact nature of the dipole anomaly. Some researchers suggest that it might not be entirely due to our motion. They propose that other factors could contribute to the observed dipole. Alternative explanations include large-scale structures influencing the CMB. Massive cosmic structures could affect the CMB in ways that mimic a dipole pattern. Studying these possibilities helps refine our understanding of the universe. Instrumental calibration plays a role in accurately measuring the dipole anomaly. Precise calibration ensures that the observed dipole is not an artifact of the instruments. High-quality data is essential for reliable analysis. Foreground contamination can also impact the dipole measurement. Local sources of radiation might distort the CMB signal. Advanced data processing techniques help separate these effects from the true cosmic dipole. The dipole anomaly provides important information about our place in the universe. By studying it, scientists can better understand the motion and dynamics of our solar system. This understanding is crucial for accurate cosmological models. Future missions will continue to refine measurements of the dipole anomaly. Improved instruments and techniques will provide more precise data. These advancements will enhance our knowledge of the dipole and its implications. Comparing dipole measurements from different missions helps validate findings. Consistency across multiple datasets strengthens confidence in the results. This cross-validation is a fundamental part of scientific research. The dipole anomaly also has implications for other areas of astrophysics. Understanding our motion relative to the CMB can inform studies of local cosmic structures. It connects cosmological observations with more localized astrophysical phenomena. Educational outreach often uses the dipole anomaly to illustrate key concepts in cosmology. Explaining how our motion affects the CMB helps people grasp the dynamic nature of the universe. This example makes abstract concepts more tangible. The study of the dipole anomaly exemplifies the detailed work required in cosmology. Each aspect of the CMB provides insights into different facets of the universe. The dipole is just one piece of the complex cosmic puzzle. As research continues, the dipole anomaly will remain a focal point. Its study contributes to the broader understanding of the cosmos. Ongoing investigations will refine our knowledge and uncover new aspects of this intriguing feature. Large-scale structure anomalies in the universe refer to unexpected patterns in the distribution of galaxies and clusters. These anomalies challenge the standard model of cosmology. They raise questions about our understanding of cosmic evolution. One such anomaly is the Great Wall, a massive structure of galaxies. It spans hundreds of millions of light-years. Its size is difficult to explain with current models of galaxy formation. Another example is the Hercules Corona Borealis Great Wall. It is one of the largest known structures in the universe. This colossal structure challenges our theories about the uniformity of the cosmos. The Sloan Great Wall is another significant anomaly. It is a large, densely packed region of galaxies. Its discovery has prompted further studies into large-scale cosmic structures. Large quasar groups are also notable anomalies. These groups contain several quasars and span vast distances. Their existence suggests that large structures formed earlier than predicted. Void regions present another type of anomaly. These vast empty spaces contain very few galaxies. They contrast sharply with the densely packed structures and pose questions about matter distribution. The existence of supervoids, like the one associated with the cold spot, adds to the mystery. These enormous voids could influence CMB temperature fluctuations. Understanding them is crucial for refining cosmological models. Cosmic filaments are another feature of large-scale structures. These vast, thread-like formations connect clusters of galaxies. Their intricate patterns challenge our understanding of cosmic evolution. Some researchers propose that these anomalies indicate variations in dark matter distribution. Dark matter is thought to drive the formation of large-scale structures. Anomalies might reflect unexpected properties or behaviors of dark matter. Others suggest that modifications to general relativity could explain these structures. Alternative gravity theories might account for the anomalies. Testing these theories is a focus of ongoing research. Advanced simulations help scientists explore these anomalies. By modeling the universe under different conditions, researchers can test various hypotheses. These simulations provide insights into the formation and evolution of large-scale structures. Observational campaigns aim to map these structures in greater detail. Projects like the Sloan Digital Sky Survey have provided extensive data. This data is essential for understanding the full extent and nature of these anomalies. Future missions will enhance our ability to study large-scale structures. Enhanced telescopes and instruments will provide more detailed observations. These missions will help refine our understanding of the universe's structure. Large-scale structure anomalies highlight the complexity of the cosmos. They remind us that there is still much to learn about the universe. Each discovery adds a piece to the cosmic puzzle. Understanding these anomalies is crucial for advancing cosmology. They challenge existing theories and inspire new lines of inquiry. Ongoing research will continue to unravel the mysteries of large-scale cosmic structures. Alignment with other cosmic structures is a fascinating area of study in cosmology. It examines how large-scale structures align with the cosmic microwave background. These alignments could reveal new insights about the universe's history and composition. One key area of focus is the alignment of galaxy clusters with CMB anomalies. Researchers study how the distribution of galaxy clusters correlates with temperature fluctuations. These correlations might indicate underlying physical processes. The Great Wall and other large-scale structures are also analyzed for alignment. Their orientation and distribution could influence the CMB. Understanding this relationship helps refine our models of cosmic evolution. Cosmic filaments, the vast threads connecting galaxy clusters, are examined for their alignment. Their intricate patterns might correspond with specific features in the CMB. This alignment could provide clues about the universe's large-scale structure. The study of supervoids and their alignment with the CMB is particularly intriguing. Supervoids are vast, empty regions that can affect temperature fluctuations. Alignments with these voids might explain certain anomalies in the CMB. Quasar groups are another focus of alignment studies. These high-energy sources can be distributed in ways that impact the CMB. Analyzing their alignment helps understand their role in cosmic evolution. The polarization of light from distant galaxies is also examined. Alignments in polarization patterns might correlate with CMB features. This study can reveal information about the universe's magnetic fields and structure. Dark matter distribution is a critical aspect of alignment studies. The invisible matter's influence on visible structures could align with CMB anomalies. Mapping these alignments helps understand dark matter's role in the cosmos. Researchers also explore the alignment of cosmic voids with other structures. These voids might have specific orientations that align with larger patterns. Studying these alignments provides insights into cosmic evolution and structure. The impact of gravitational waves on cosmic alignments is a growing field. These ripples in space-time might influence the distribution of large-scale structures. Detecting their effects helps refine our understanding of gravity. Advanced simulations play a crucial role in studying alignments. They model the universe under various conditions to predict possible alignments, comparing simulations with observations tests different cosmological theories. Observational data from projects like the Sloan Digital Sky Survey is essential. These extensive surveys map the universe's structure in great detail. This data provides a foundation for studying alignments with the CMB. Future missions will enhance alignment studies. Improved instruments will provide more precise data on cosmic structures. These advancements will help detect subtle alignments and refine our models. Interdisciplinary collaboration is key to studying alignments. Combining insights from different fields like astrophysics and particle physics leads to comprehensive understanding. This collaboration drives innovative research. Alignment studies are vital for understanding the universe's large-scale structure. They reveal how different cosmic elements interact and evolve. Ongoing research in this area continues to uncover the mysteries of the cosmos. Implications of multiple anomalies in the cosmic microwave background are profound for cosmology. These anomalies challenge the standard model and suggest that there might be unknown factors at play. Understanding them could lead to groundbreaking discoveries in physics. The presence of multiple anomalies, such as the axis of evil, the cold spot, and the dipole anomaly, indicates that our current theories might be incomplete. Each anomaly requires careful investigation to determine its cause. Together, they suggest a more complex universe than previously thought. If these anomalies are confirmed to be significant, they could point to new physics beyond the standard model. This might include unknown particles, forces, or interactions. Discovering these elements would revolutionize our understanding of the universe. One implication is the potential need to revise our theories of cosmic inflation. Anomalies could indicate that the early universe behaved differently than current models predict. Adjusting these models could provide a more accurate picture of cosmic history. The anomalies might also suggest variations in the fundamental constants of nature. Changes in constants like the speed of light or gravitational constant over time could explain some of the observed anomalies. This possibility opens new avenues for theoretical research. Multiple anomalies could imply the existence of large-scale structures or patterns in the universe. These structures might influence the CMB in unexpected ways. Understanding their impact is crucial for refining cosmological models. The idea of a multiverse gains traction if anomalies are interpreted as interactions with other universes. This concept suggests that our universe is one of many, each with its own properties. Exploring this idea could transform our understanding of reality. Anomalies might also reflect unknown properties of dark matter and dark energy. These components make up most of the universe's mass-energy content, but remain poorly understood. Studying anomalies can provide clues about their nature and behavior. The alignment of anomalies with other cosmic structures suggests a deeper connection between the CMB and the large-scale universe. This alignment could reveal new insights into how the universe's structure evolved. It emphasizes the need for comprehensive multi-scale studies. Instrumental and calibration issues must be ruled out to confirm the significance of anomalies. Ensuring high-quality data and accurate measurements is essential. Any errors in instrumentation could lead to false conclusions about the nature of these anomalies. Future missions with advanced technology will help resolve questions about anomalies. Enhanced sensitivity and resolution will provide clearer data. These missions are critical for determining whether the anomalies are real or artifacts. Collaboration across disciplines is necessary to fully understand the implications of multiple anomalies. Combining expertise from cosmology, particle physics, and other fields will lead to more robust conclusions. This interdisciplinary approach is key to addressing complex scientific questions. Public interest in cosmic anomalies highlights the importance of science communication. Engaging the public with these mysteries fosters a broader appreciation for scientific research. It also inspires the next generation of scientists. The study of multiple anomalies drives innovation in both theory and observation. Each anomaly presents a challenge that pushes the boundaries of our knowledge. Addressing these challenges is crucial for advancing cosmology. Ultimately, the implications of multiple anomalies remind us of the universe's complexity. They highlight how much we have yet to learn and the potential for new discoveries. Ongoing research will continue to explore these fascinating features of the cosmos. Ongoing studies and projects in cosmology are dedicated to understanding the cosmic microwave background and its anomalies. These efforts are crucial for advancing our knowledge of the universe. Researchers are continuously developing new methods and technologies to improve observations. The Atacama Cosmology Telescope continues to provide valuable data. Located in the high Chilean Andes, it offers high-resolution maps of the CMB. This ground-based telescope is essential for studying small-scale fluctuations. The South Pole Telescope, operating at one of the coldest places on Earth, focuses on CMB polarization. Its unique location minimizes atmospheric interference. This telescope helps improve our understanding of cosmic inflation. The Simons Observatory, a state-of-the-art facility, is under construction. It will deploy several telescopes to measure temperature and polarization with unprecedented precision. This project aims to refine the values of cosmological parameters. Lightbird, a planned satellite mission, will map the polarization of the CMB across the entire sky. Its goal is to detect B-mode polarization patterns. These patterns provide crucial evidence for the theory of cosmic inflation. The European Space Agency's Planck satellite, although its mission ended in 2013, still contributes through its extensive data archive. Researchers continue to analyze Planck's data to extract new insights. This archive remains a goldmine for cosmologists. The BICEP array, located at the South Pole, aims to detect primordial gravitational waves. Its sensitive instruments focus on CMB polarization. These observations are key to understanding the early universe. The Dark Energy Survey complements CMB studies by mapping the distribution of galaxies. It helps understand the large-scale structure of the universe. This survey provides context for interpreting CMB anomalies. The Square Kilometre Array, an ambitious international project, will be the world's largest radio telescope. It will study the universe in unprecedented detail. This array will contribute to CMB research by examining cosmic structures. The James Webb Space Telescope, set to launch soon, will observe the universe in the infrared. Its capabilities will shed light on the formation of the first galaxies and stars. These observations will enhance our understanding of the CMB's context. Supercomputing facilities like the National Energy Research Scientific Computing Center support CMB research. These powerful computers run complex simulations and analyze vast datasets. They are crucial for modeling the universe and interpreting observations. International collaborations play a significant role in ongoing CMB studies. Projects like CMB-S4 bring together scientists from around the world. This collaboration ensures a comprehensive approach to solving cosmological mysteries. Public and private funding is vital for these projects. Organizations like NASA, the European Space Agency, and the National Science Foundation provide essential support. This funding drives innovation and discovery in cosmology. Educational initiatives linked to these projects help train the next generation of scientists. Graduate programs and research opportunities in cosmology are expanding. These initiatives ensure the continuity of high-quality research. Public engagement through science communication is also a focus. Projects aim to share their findings with a broader audience. This engagement fosters a greater appreciation for cosmology and its discoveries. Ongoing studies and projects in CMB research represent the cutting edge of cosmology. They are essential for addressing the fundamental questions about the universe. These efforts will continue to push the boundaries of our understanding. New data from recent missions have provided fresh insights into the cosmic microwave background. These missions have achieved unprecedented precision and depth in their measurements. The results are helping to refine our understanding of the early universe. The Planck satellite's final data release offered a comprehensive view of the CMB. It provided high-resolution maps of temperature fluctuations and polarization. This data has been instrumental in testing and confirming cosmological models. One significant finding from Planck is the improved measurement of the Hubble constant. The value derived from CMB data continues to differ from local measurements. This discrepancy remains a key challenge in cosmology. The South Pole Telescope has also contributed valuable data on CMB polarization. Its high sensitivity has allowed for detailed studies of E-mode polarization. These measurements help constrain models of cosmic inflation. New observations from the Atacama Cosmology Telescope have enhanced our understanding of small-scale fluctuations. These detailed maps offer insights into the distribution of matter in the universe. They are crucial for studying the large-scale structure. The BICEP-Keck array continues to search for B-mode polarization. Recent data have provided tighter constraints on the possible signal from primordial gravitational waves. This ongoing work is vital for testing inflationary theories. The Dark Energy Survey, while not focused solely on the CMB, provides complementary data. Its maps of galaxy distribution help contextualize CMB findings. This synergy enhances our overall understanding of the cosmos. LIGHTBIRD's upcoming mission promises to deliver new polarization data. By mapping the CMB across the entire sky, LIGHTBIRD aims to detect subtle B-mode signals. This mission will significantly advance our knowledge of the early universe. The Simons Observatory is set to revolutionize CMB studies with its advanced instrumentation. Early test results show promise for achieving unprecedented measurement accuracy. The observatory will explore both temperature and polarization fluctuations. Recent balloon-borne experiments like SPIDER have also provided new insights. Operating at high altitudes, these experiments reduce atmospheric interference. Their data contribute to the overall picture of the CMB. The James Webb Space Telescope, though primarily focused on the infrared universe, will offer valuable data. Its observations of early galaxies and stars will help refine models related to the CMB. This context is essential for interpreting CMB anomalies. New data from these missions are continually being analyzed. Researchers are developing sophisticated algorithms to process and interpret the findings. This ongoing work is crucial for extracting meaningful information from vast datasets. International collaborations enhance the impact of new data. By sharing resources and expertise, scientists can cross-validate findings. This collaborative approach ensures the robustness of conclusions drawn from the data. Publications based on recent data are shaping the current discourse in cosmology. Peer-reviewed papers present new theories and refine existing models. These publications are essential for advancing scientific knowledge. Future missions building on this new data promise even greater discoveries. Enhanced technology and refined methods will continue to push the boundaries of our understanding. The study of the CMB remains a dynamic and evolving field. The influx of new data from recent missions reaffirms the importance of continued exploration. Each new piece of information adds depth to our cosmic knowledge. These efforts drive us closer to unraveling the mysteries of the universe. Collaboration among international research teams is essential for advancing our understanding of the cosmic microwave background. These partnerships combine expertise, resources, and diverse perspectives. Together, they tackle complex challenges that no single team could address alone. One key example is the Planck collaboration, which involved scientists from multiple countries. This teamwork was crucial for the mission's success, leading to groundbreaking discoveries. Shared knowledge and technology amplified the impact of the findings. The Atacama Cosmology Telescope benefits from international collaboration as well. Researchers from around the world contribute to its operations and data analysis. This global effort enhances the telescope's scientific output. The Simons Observatory is another collaborative project. It brings together institutions from several nations to build and operate advanced telescopes. This cooperation ensures that the observatory achieves its ambitious scientific goals. LIGHTBIRD, a Japanese-led mission, exemplifies international cooperation. Scientists from Europe and the United States are deeply involved. This collaboration enhances the mission's capabilities and scientific reach. The BICEP-Keck array involves researchers from various countries. This team works together to study CMB polarization with high precision. Their combined efforts are essential for advancing our understanding of cosmic inflation. The South Pole Telescope collaboration includes institutions from the United States and other nations. This project benefits from shared resources and expertise. International teamwork helps optimize the telescope's performance and data quality. The Dark Energy Survey is another example of successful international collaboration. Researchers from numerous countries work together to map the universe's structure. This joint effort provides valuable context for CMB studies. The upcoming CMB-S4 project will rely heavily on global cooperation. Scientists from multiple countries are involved in its planning and execution. This collaboration is crucial for achieving the project's scientific objectives. Balloon-borne experiments like SPIDER also involve international teams. These collaborations enhance the design, execution, and analysis of the experiments. Sharing knowledge and skills improves the overall quality of the research. International conferences and workshops facilitate collaboration. These events allow researchers to share their latest findings and discuss new ideas. Networking at these events fosters partnerships and joint projects. Collaborative publications are a significant outcome of international research. Jointly authored papers combine insights from different teams. These publications are vital for disseminating new knowledge and advancing the field. Funding from multiple countries supports these collaborative efforts. International funding enables large-scale projects that would be difficult to finance individually. This shared investment drives scientific progress. Training and education programs benefit from international collaboration. Researchers exchange knowledge and train the next generation of scientists. These programs ensure a continuous flow of skilled experts in cosmology. The future of CMB research depends on continued international collaboration. As new missions and experiments are planned, global partnerships will be more important than ever. Working together, researchers can achieve breakthroughs that push the boundaries of our understanding. Collaboration among international research teams exemplifies the spirit of scientific inquiry. By uniting across borders, scientists address the universe's most profound mysteries. These cooperative efforts will continue to shape the future of cosmology. Recent publications and findings have significantly advanced our understanding of the cosmic microwave background. These studies have provided new insights into the early universe and its evolution. They highlight the ongoing progress in cosmological research. One notable publication analyzed the final data released from the Planck satellite. This comprehensive study refined measurements of the universe's age and composition. It confirmed that the universe is approximately 13.8 billion years old. Another important finding from Planck's data involves the Hubble constant. The study revealed a persistent discrepancy between the CMB-derived value and local measurements. This tension remains a central topic in cosmology, prompting further investigation. Recent work from the South Pole telescope has focused on CMB polarization. These findings have provided tighter constraints on models of cosmic inflation. The data supports the theory that inflation played a crucial role in the early universe. The BICEP-Keck array collaboration published results on B-mode polarization. Although no definitive detection of primordial gravitational waves was made, the study set strong upper limits. This work continues to guide theoretical models and future experiments. The Atacama Cosmology Telescope's latest findings have enhanced our understanding of small-scale fluctuations. Detailed maps of the CMB have been produced, offering insights into the distribution of dark matter. These results are essential for modeling the large-scale structure of the universe. Publications from the Dark Energy Survey have also made significant contributions. By mapping the distribution of galaxies, these studies provide context for CMB observations. The survey's findings help to better understand the universe's expansion and the nature of dark energy. A recent analysis of data from balloon-borne experiments like SPIDER has provided valuable polarization measurements. These high-altitude observations reduce atmospheric interference, leading to clearer data. The findings contribute to our understanding of the early universe's conditions. New theoretical papers have explored the implications of CMB anomalies. Researchers are developing models that might explain these unexpected features. These studies are crucial for testing and refining our understanding of cosmic inflation and dark matter. Collaborative publications have highlighted the importance of international research efforts. Joint studies combine data from various missions and telescopes. These comprehensive analyses provide a more complete picture of the CMB and its implications. Recent findings have also focused on the effects of gravitational lensing on the CMB. Studies have shown how massive cosmic structures distort the background radiation. This research helps map the distribution of matter in the universe. Several papers have discussed the potential role of exotic physics in explaining CMB anomalies. These studies suggest that new particles or forces could influence the early universe. The findings open exciting possibilities for future research. Advancements in data processing techniques have been documented in recent publications. improved algorithms are enabling more precise analysis of CMB data. These methodological innovations are enhancing the accuracy and reliability of cosmological findings. Ongoing research has also addressed the calibration and instrumentation issues in CMB studies. Recent papers outline strategies for minimizing errors and improving data quality. These improvements are crucial for ensuring robust scientific results. The role of large-scale structures in shaping CMB anomalies has been explored in recent studies. Researchers are investigating how galaxy clusters and voids might affect the background radiation. These findings are helping to refine our models of cosmic structure formation. Recent publications and findings demonstrate the dynamic and evolving nature of cosmological research. Each new study builds on previous work, pushing the boundaries of our knowledge. The continuous flow of discoveries is essential for unraveling the mysteries of the universe. Future directions in research on the cosmic microwave background are focused on addressing unresolved questions. These efforts aim to refine our understanding of the early universe. They also explore potential new physics beyond the standard model. One key area of future research is the detailed study of CMB polarization. Upcoming missions and instruments will aim to detect B-mode polarization. This could provide definitive evidence for cosmic inflation. Researchers will continue to investigate the Hubble constant discrepancy. New data and methods will help determine whether this tension points to new physics. Resolving this issue is crucial for understanding the universe's expansion. Improving the sensitivity and resolution of CMB measurements is another focus. Advanced technology will enable more precise observations. These improvements will help detect subtle features in the CMB. Exploring the nature of dark matter and dark energy remains a priority. Future studies will use the CMB to gain insights into these mysterious components. Understanding their properties is essential for a complete picture of the cosmos. Simulating the universe's evolution with greater accuracy is also important. Enhanced computational power will allow for more detailed models. These simulations will help test theoretical predictions against observed data. Future missions will aim to map the CMB with unprecedented detail. Projects like CMB S4 and Lightbird will provide new data. These missions will enhance our understanding of the universe's structure and history. Investigating the impact of large-scale structures on the CMB will continue. Researchers will study how galaxy clusters, filaments, and voids influence the background radiation. This work will refine models of cosmic structure formation. Collaboration between international research teams will be crucial. Joint efforts will pool resources and expertise. This collaboration will drive forward the field of cosmology. Advancements in data processing and analysis techniques will play a significant role. New algorithms will improve the accuracy and reliability of CMB data. These methods will help extract more information from observational data. Addressing instrumental and calibration challenges is another important direction. Ensuring high-quality measurements is essential for robust results. Future projects will focus on minimizing errors and biases. Studying anomalies in the CMB will remain a key area of interest. Researchers will investigate features like the cold spot and axis of evil. Understanding these anomalies could reveal new aspects of the universe. Theoretical developments will guide observational strategies. New models will predict specific CMB features to look for. These predictions will shape future missions and experiments. Public engagement and education will continue to be important. Communicating scientific discoveries to a broader audience fosters appreciation for cosmology. It also inspires future generations of scientists. Future research will explore the potential for exotic physics. Studies will investigate whether unknown particles or forces influence the early universe. Discovering such elements would revolutionize our understanding of physics. The future of CMB research is bright and full of potential. Each new discovery adds depth to our knowledge of the universe. Ongoing efforts will continue to unravel the mysteries of the cosmos. In this video, we delved deep into the intriguing concept of the cosmic microwave background, starting with an introduction to the axis of evil in astrophysics. We explored the mysterious alignment of the CMB's temperature fluctuations and discussed its significance in the context of cosmology. We then moved on to the background of the CMB, understanding how it serves as a snapshot of the early universe and its role in validating the Big Bang theory. We also covered the initial observations that led to the discovery of the CMB, highlighting the pioneering work of scientists who identified this faint radiation. The methodologies used in these discoveries were examined, emphasizing the precision and innovation involved in CMB research. The early reactions from the scientific community were also discussed, showing how initial skepticism gradually turned into widespread acceptance as more evidence came to light. Our discussion included the detailed explanation of anisotropies in the CMB and their significance. These tiny temperature fluctuations provide a wealth of information about the universe's structure and composition. We also covered the theoretical predictions of the CMB, explaining how different cosmological models predict specific features in the CMB data. The video touched on the role of the CMB in cosmology, highlighting how it has become a cornerstone in our understanding of the universe. We examined various anomalies observed in the CMB, such as the cold spot and the dipole anomaly, and discussed potential explanations for these features. These anomalies challenge our current models and suggest there may be new physics waiting to be discovered. We also explored the methodologies used to detect these anomalies, including advanced statistical techniques and simulations. The significance of these anomalies was a major focus, as we discussed how they might indicate new physics beyond the standard model. We also looked at the large-scale structure anomalies and their implications for our understanding of cosmic evolution. Collaboration among international research teams was highlighted as a crucial factor in advancing CMB research. The pooling of resources and expertise from around the world has driven many of the significant discoveries in this field. We also reviewed recent publications and findings, which continue to refine our understanding of the CMB and its anomalies. Looking to the future, we discussed the exciting directions in CMB research. Upcoming missions and advanced technologies promise to provide even more detailed data, helping to resolve ongoing debates and uncover new cosmic phenomena. These future directions underscore the dynamic and evolving nature of cosmological research. In conclusion, the study of the cosmic microwave background remains one of the most fascinating and productive areas in astrophysics. From the initial discovery to the latest technological advancements, each step has brought us closer to understanding the origins and structure of our universe. The CMB continues to be a rich field of exploration, promising many more discoveries in the years to come. If you enjoyed this video, please like and subscribe to our channel. Your support helps us continue to bring you in-depth explorations of fascinating scientific topics. Don't forget to check out the rest of our videos for more insights into the wonders of the universe. Thank you for watching, and we look forward to bringing you more exciting content soon.